Right. Welcome everyone all over the world. It's the year 2023 and we are in the month of October. And we have again a very exciting meeting related to Forth and CPUs, Forth stack-based CPUs and other things. And if you want to have a look at the schedule, go ahead and go to forth2020.org, and there's a menu item Zoom meetings, and you will find the table of content, the schedule for all the meetings that we had, and also for today's meeting. And yeah, we have exciting talks, and our first talk is from Phillip Oraes, and he will talk about the RTX 2000, which is a very exciting stack CPU. And we learn a lot about that, I guess, in your talk. So, George, are you with us?
Yes, hello.
Then the stage is yours, and you can share your screen. And yeah.
Okay. Sorry. Yeah. Good evening. Good morning. Good afternoon. Good evening, everyone. So yes, I have this. I prepared this slide. So yeah. I will talk about the RTX 2000 board. So please excuse my slide. And yeah. First is it has an Harris RTX 2000. This is just an overview. So it's running at 10 megahertz and it's a 16-bit stack machine, and it's a dual stack architecture, which means data stack is 16-bit wide into 56 words, and return stack 21-bit wide and also 256 words. And it has two address bus and data bus. Address bus, there's a ASIC address bus, which is 3-bit wide, and for memory, it's 19-bit wide. And for data bus, yeah, both are 16-bit wide for ASIC and memory. And yeah, so for my board, it's actually from MPE. So it's a called RTX 2000 power board, which has here we can see from the left side, here's the RTX processor. Then it has a 64 kilobyte RAM, which is this, which composed of two this static RAM, and it's expandable to 512, as well as the ROM. It has a 128. As of the moment, it has 128 kilobyte ROM, which consists of two EEPROMs, which is this, and it's also expandable. And it has two serial ports using 853 chip, which is RS232 and the RS485, which is here. And there's also a SCSI interface using this chip. And there's also parallel IO using this chip, which is this port. And there's a 3-channel timer, which generates a time for the serial. And there are two expansion connectors, which is this passive backplane, and there's a pin here for local daughter board, but this is empty as of the moment. And there are also reprogrammable logic for memory and IO decoding, which are two lattice GAL chips. I think it's these two, and Altera EP310. So yeah, this is the board components. And regarding the Fort that is running, it's called ROM RTX 2000 ROM Power Fort, which is this is the when we use the Tera term. And yeah, as the document state, it just occupies very small portion of the two EEPROMs, and it's a complete 483 environment. And yeah, so how do we program this board? And it was mentioned 3 ways. So first is host PC as text file server. So we have host PC connected to the board using null modem. And we have the suggestion is to use communication software like Procom, Crosstalk, Mirror, and we just use ASCII text file to send it to the board, and we can compile it and get the binary image into hex, and use the EEPROM writer to write this to the EEPROM, and we can replace this. Another method is called host PZ running a Fort file server. So same setup, but using a different software, which is MP's cross-comparative Excel, where we can use ASCII text file for source or Fort screen file. And this shell also communicates with the ROM writer. So it will write the ROM and we can replace the ROMs. And the third one is, it was mentioned, it can run standalone using a terminal. So the board, we need to connect a SCSI, a hard disk through SCSI and a possible floppy disk using the power port, and just using some terminal emulator like Hyper Terminal, Minicom, TeraTerm. And these are some questions that, and so what's the reason why I had this board? So it's just my interest on how Fort engine were programmed using Fort during their prime. I think RTX was those moment. Then my goal is to build system that to build a system that utilizes the full capability of the RTX. Like it was mentioned, it's capable for image processing, robotics, and Fort laptop is just my one of my imaginations. And my current plan is to try some the intended devices like a SCSI drive, RS485 communication, and floppy drive VGA. And also maybe later I want to try some modern devices, connect modern devices like Wi-Fi, touchscreen, and SD card. And so for the demo, sorry that it's very simple, but let me share my screen to the other PC, which is connected to the board. Can you see my screen? Then let me start my video. So my video now is showing the board with the breadboard. Can you see the
We see the TeraTerm window and an editor to the right, or we don't see a video.
It's actually the video of another account, which is Geo. Or let me open this camera from here.
Oh yes, I see it. Geo.
That's because I use two accounts. Sorry. But so in the camera of this account, it shows the RTX board with the breadboard with LED. So, but my demo is just
I can't see any breadboard. I don't know what you guys are looking at. I just see the
on Geo. It's another user, another account on the Zoom.
I went through them all. I couldn't see anything that showed a breadboard. Oh yeah, I found it. Thank you. I'll shut up now.
So that's the my board. The RTX is connected to a breadboard with LEDs, 4 LEDs, just the nibble. And for my demo, it's just I have this code in text. Actually, I was planning to make a better demo, but I underestimated. So just let me show this very simple demo. So as you can see, I use TeraTerm, and it's now showing it's connected to the board and it's waiting now. So, and let me drop this demo text So to do that, I need to command type the upload, and then it asks, it's waiting for the file. Here it says Procom, but good thing TerraTerm has this. Yeah, we can drop the file also like this, and then TerraTerm will ask. Then I just press OK. Then upload finish. Then I have this 3 functions of 3 words. So let me turn on some LED like first. So I will write. Then it will turn on. Then then other functions like shift left IO. Then it's just shifting the LED, and then shift right IO. It's just shift the LED. So sorry that's just my demo for today, but I plan to make more once.
Fantastic. Excellent.
Thank you. But so I think that's all for my presentation today. If there's any questions, I'll try my best to answer.
Thank you very much. So it reminds me of the old times when we did RTX 2000 programming a long time ago. I appreciate that.
So
Are there any questions?
That's the spirit of Forth. This is the spirit of what we expect from any of you that wants to participate in next meetings. There is nothing to prepare, nothing fancy. Just show us, hey, guys, I was working with this board. It runs. I am very happy because this is a super old system. It's a really retro computing. And for the first time, somebody shows us the RTX 2000. So it's amazing.
That's a nice board layout. Did you lay the board out yourself?
Sorry, you mean the power board?
The CPU board.
Sorry, no, I bought it. Actually, this is made by MPE.
Oh, right.
MPE.
Is what's the signals on the DIN connector? What's available?
Let me share my other screen so I can understand. Let me share
the big white DIN connector at the bottom. I think that's SCSI, right?
Yes, is that address and data buses?
Do you mean this lower?
Yes, it's a DIN 4100 something, 92 or something.
96.
This one.
96 pin connector.
96, excellent.
Yeah, that's the let me go. It's the for
expansion,
the
expansion bus.
Expansion, yes. And this pin has the pins for memory address and memory data, and the ASIC address and ASIC data bus. But one of my plan is also to try to use the ASIC data, and because most of these peripheral ICs are connected to the memory, and it's a memory map I also. But for the ASIC bus, it's mentioned that it's an IO that is very fast because it's connected directly to the RTX. So it's maybe I'll try to see if I can utilize it with something.
Nice. Other questions?
Can you type words and show us what the current dictionary is on that device?
Yeah. Sorry, let me share again my other screen. Share screen. Can you see my screen?
Yep.
Yeah.
Yeah. Words. It has some. Sorry, but yeah, these are the words, and yeah, there's some vocabulary. So yeah.
So is this like a 433 standard equivalent? Oh yeah, there it is, 433. Yeah.
Sorry, I'm still trying to yeah, learn more about these words, but yeah.
So do you have a handbook or source code of the system?
Yeah, I had these two manuals.
Great.
Comes and yeah, and it has some explanation like what, but yeah, I can only do this during evenings after work or weekends, so progress is a bit slow, but yeah.
Cool.
Yeah, actually, I was attempting to make this delay so that, but unfortunately, it didn't work. Maybe, yeah, I misunderstood something. So that's why.
Here you can see I have a similar card, not an RTX, but this is the bus, the DIN 4000. It's very common, and this is an Euro card. I think George has a 1.5 of the size of an Euro card.
Yes.
Because he has this SCSI extension on board. It's very nice.
Yeah, it has this SCSI, yeah, inside.
It's a very powerful board for its time. It was an amazing technology, having all this development system in such a single board.
As for the delay, I think what I saw was something like 100 for next. I mean, this runs really, really fast. So 100 for next is like 300 instructions or so, and that should not delay it much.
Actually,
I see you nested a couple of times, yeah, but maybe, yeah, we will see.
I see. Yeah, actually, I did this just today, and when I tried, it's not working properly. So yeah, actually, DLNS means delay nanosecond, and delay microsecond, and delay millisecond, and delay seconds. But
yeah, I see.
Seems it did not work as expected, so I just skipped this.
All right. So, are there any additional questions to George?
Does the RTX 2000 execute a single fourth primitive in one clock cycle?
Sorry, I did not go into that deep yet, but yeah, I'm not very sure.
Low level work, like dupe or plus or something, because you said it was the clock speed was 10 megahertz, I think.
Yes, 10 megahertz as it's based on the in the document it's mentioned.
Andrew, on the data sheet of these chips, these are all descendants of the Novix. We were talking about this before, but the RTX has more power than the Novix and was able to execute burst of up to 15 MIPS, explained on the data sheet with the 10 megahertz clock.
Right.
So this means that it was able to execute up to approximately 4 to 5 instructions in a clock cycle.
Mhm.
And the mean was three instructions per cycle. It's remarkable for that time. It was an outstanding technology.
Mhm. Yeah. So interesting. There's some discussion going on in the chat in that the RTX 2000 is still available if you want to buy it at DigiKey and what is it? Rochester Electronics. And you have to buy a couple of them, batches, but the unit price is not as high as I expected, because my last knowledge was there was only the RTX radiation hard version available, which costs like a couple of $100 a chip. But now it's down to like $30 a chip, but you have to buy a batch. So, and there's also the suggestion in the chat that maybe we do a group buy and buy a batch within the group, and then everyone can get a small supply as he or she wants. So I think that's an interesting idea. So yeah, maybe we follow up on that later on.
It is really.
So additional questions to George? Okay, so thank you again. Great talk. And I appreciate the status reports. This is what I did, and I give a short demo, and then everyone gets excited about that. So thank you again for this.
Thank you.
So let's proceed. And here is the time for Brad talking about his ForthTTL CPU. And yeah, Brad, are you with us? I think what I wanted to say earlier, when we did the sound check, maybe if you just keep the video on for a short time and then switch it off, this would bring enough bandwidth so that your voice will be fine. Brad.
Okay, I'll do that. You recall from previous meetings that my system does not be able to support both the video and a shared screen. But I'll speak for a few minutes with just the video on. This is actually probably not a fourth CPU, but I can make an argument that it is. And it amazes me that this seems to be the longest lasting of all the work I've done, because every year or two I get a new query about the pathetic instruction set computer, otherwise known as the PISC, P-I-S-C. And this was a result of having unsupervised students in grad school. We were studying computer architecture. I was learning about the PDP-11, and I just started working in this really nifty language called Forth. And we began to wonder, seeing more and more code. This is the era of the complex instruction set computer, the CISC, and more of the application was being moved into microcode. And we thought, how do we accelerate this so that the entire application is written in microcode? And thought, well, this threaded code idea might be a way to might provide the instruction set that we need. So I hope that was enough audio. I'm going to try sharing my screen now. It would be that one. Allow.
Right, that works.
Is that coming through?
Yep.
Okay, I'll shut down the video. So we had this interesting idea, but a typical micro program machine is going to have maybe 100 bits of micro instruction, very wide micro instruction store. And we were trying to think of how could we get that down to, say, 16 bits of micro instruction. And it took a while. I kept coming back to it after years, and we finally did come up with it. or I finally didn't come up with it. My friends had graduated and gone on to more productive things. So, oh, good. So what we have here, the PISC, the pathetic instruction set computer, is either you're looking at it as a microcoded CPU, by which I mean all of the bits in the instruction are controlling hardware signals. They're controlling, they're not packed into some efficient utilization of the memory. Each bit is a hardware line. So this is either a microcoded CPU with a very short micro instruction, a 16-bit micro instruction, which, as anyone will tell you, is pathetic. Or it can be viewed as, forget the micro instruction, it's a hardwired CPU. There is no micro instruction store separate from the main instruction store. A hardwired CPU with a very peculiar instruction set. Or in other words, pathetic. So that led to calling it the pathetic instruction set computer, which is, I think, probably the most idiotic instruction set of any computer I've ever seen. It has no branch or conditional branch instruction, for example. It has no way to rotate or shift right. And it can shift left, but to rotate left, you need multiple instructions. There's no subroutine call. But in a threaded Forth environment, you don't need a subroutine call. You're doing it all. It's the same reason that Forth works fairly well on an 1802, and other languages don't really work well with that processor. So what I came up with eventually was this. That's it. That's the entire central processing unit. It's got a 16-bit ALU. It's got a 16-bit register file with 8 registers, and an instruction register, and some glue logic, some additional functions. You will note the absence of a program counter. The program counter is register 7 in the register file. There's the PDP-11 influence. And the microinstruction word is very simply reading from bit 15 down to bit 0. There's a memory read strobe, a memory write strobe. Those go out to the external memory. A reg, which selects one of the registers in the register file. It selects the A address, which is input only. That's a very strange register file. It's either viewed as a 3-port or a 4-port register file, because we can read one register, write a different register, and both read and write a third register. So 3 bits to select the A register, which is named after the ALU, in this generation named after the ALU port that it's using. 3 bits for the F register, which is where the F output, the function output of the ALU is going. A ST is the instruction to latch the status resulting from this instruction. The CYN is a 2-bit selector because the carry input to the ALU sometimes needs to have a carry if you're doing multiple precision arithmetic, but also sometimes need to have a forced carry or a forced 0-bit or a forced 1-bit. So, and to read it as a status register, to read the status back into the ALU, I also have the A equals B as one of the choices for the carry input. And then the ALU function itself is 5 bits. Those are just 5 bits of the 74181 ALU. Now, how does this thing work? It alternates between a fetch cycle and an instruction cycle, where the instruction cycle comes from the program. The fetch cycle is hardwired and does this. Address register 7 is output to the A bus, which is the address bus. That also goes into the ALU. The ALU has a function of A plus carry. And if the carry is forced to be 1, that's A plus 1. And that's your auto incrementer, your increment of the instruction counter, or the program counter, excuse me. So the ALU increments register 7 by 1, and simultaneously the register 7 is output to the memory. The data from the memory goes into the instruction register. Now, with one small change, this is hardwired. This is not a part of your application program, but with one small change, it is a part of your application program. It's the memory read function. And memory read is the exact same thing we just did, except instead of going into the instruction register, it goes to the C port on the register file. And this actually is the tiny little bit of onboard hardware that isn't being done by micro instruction bits. Arguably, it should have had 17 bits of micro instruction because there's two different functions being used here. One is the store function for the instruction register. The other one is the store function for the R7 in the register file. So I cheated to the extent of 1 bit. This also can be memory read with post increment. That's in fact what you see here now, the A+1. So if you want to traverse a table or move up and down a stack, there's a post increment function. And it can be load immediate in exactly the same manner as the PDP-11. Use register 7 as the address register in your own instruction. Cause the ALU to increment it, but the data is stored into the register file rather than into the instruction register. Proceeding. No, wrong button. There we go. Then there's the memory write. Again, the address side of this is totally unchanged. In this case, comparing with the previous one for a moment, looking at the 4-to-1 multiplexer at the upper right, and I got it wrong there. I didn't actually program the post increment. So that is a memory read without post increment, and this is a memory write without post increment. And the difference is we're putting a 0 into the carry input instead of a 1. And with the memory write instruction, the C register of the register file is read out of the register file and written to memory. The C register address, the address selector for what that port's going to use is always 0. So register 0 is the memory data register in both directions. You want to write memory, you have to put the desired data into register 0 and then do a write instruction. You want to read memory, you do a read instruction, and then you have to get your data out of register 0 into one of the other registers, which actually is just another instruction. Oops, there. I'm actually going to come back to this. Well, no, I'll stay with the order I chose. ALU functions that don't require memory access. This is an example of a single operand ALU instruction. It's output from the B port, fed into the ALU, and possibly combined with the other B port, the other ALU port, but we'll get to that. And in this example, I've just chosen the one of the 16 functions available for arithmetic functions on the ALU, and that's A plus carry. And if you think about that, that's a left shift and bringing what the Z80, I think, used to call the left shift through carry. I may be misremembering that, or excuse me, rotate through carry. But this shifts the ALU one place to the left and then brings whatever the carry is into the lowest bit. There are several such instructions there. You can do 2's complement. You can do logical inversion. Shift, you can clear the clear a register all through ALU functions. For dual operand ALU functions, this is the data path, and this is an addition with carry, add with carry. The B register on the register file is output to the bus, and that goes to the ALU. The C register of the register file, which is normally a different register, is output to the data bus, the D bus. That also goes to the ALU. And the result goes back in and replaces that first register. So if I'm, because, well, actually it doesn't have to. Sorry, I'm thinking ahead to the next generation. Sure, I'll come back to that in a moment. But the third register is output and stored in the register file. So that right there is the add with carry. And of course, to add without carry, you simply select that the carry is 0 instead of the carry input to this part of the board. So that's what it looks like. I actually found this in a desk drawer before this talk. And everything to the, not to the left of the center line, including those 2 small chips and the parts, is the processor. Everything on the right side is the memory and the I/O. It takes a 2651 UART. And it also talks to a very peculiar video display that I have that plugs into that edge connector. If you look closely, I don't know how this appears on your screens, but the date on those EEPROMs is September 11th, 1993. That's the last time I've tested this unit, and I'm curious to see if the EEPROMs have held the data. But because there's a lot of testing still to be done to make sure this survives storage, I didn't think I was going to have it for today. I am working on a simulator for this board. I have a software simulator for what is currently the PISC-1 and is what is going to be the PISC-1A, and eventually I may carry it into the next generation. But that's it. I can't do it. No, I don't think the pointer shows up when I do it this way. If the pointer is showing, and I can't tell because I'm looking at my original, the registers over here, the chips over here on the left edge are the ALU, and the next two columns of chips are the register file. So that leads us to some weird instructions. But let's talk about a couple of fourth primitives where we arbitrarily have decided the PC, the program counter being 7 and the memory data register being 0, those are forced by the hardware. The other four are arbitrary choices. The instruction pointer for threading, I've used register 6. Return stack pointer and parameter stack pointer are 3 and 2, and the temporary register W is register 1. And for next is 3 of these instructions. There's a memory read cycle that uses the IP as the address, also stores the updated A+1 value back into IP. So that's use IP as the address for the read, and then increment that and store that back into IP. The second instruction in next is another memory read, except now the data is what you just read. Since we're reading from a thread of 16-bit addresses, the data register is used to provide the address bus, and what is read back goes into the W register. And I have actually, I believe it. Well, anyway. And then finally, that data, which is another address, this is indirect threaded code. That data is read into the program, or copied into the program counter, and there you go. You've started your next word. Skipping do : for a moment, I'm going to save some time and not talk about a couple of these. I left this an exercise for the student, as we used to say. The exit function is memory read from the return stack. So use the RP register as providing the address. Increment that address because it's a push down stack, and store the incremented address back into RP. So that basically pops the return, whatever is on the return stack, the topmost item, into the memory data register, and then continues. And the next instruction, MD address, memory data register provides, which we just read from the return stack, provides the address for the next instruction. That is not a memory read cycle. Notice there's no MRD in that leftmost column. This just is copying the memory data register into the IP register. So memory data source, IP destination, and just copy with no other function, just A. A is a function of the ALU, and then we're prepared to do the 3 instruction next from above. I think I could bore you to tears going through more of the instructions, so I'll just leave it at those for the moment. Now, I talked about a tweak I wanted to make. Why I'm not entirely satisfied with that. It occurred to me after wire wrapping this prototype, and it's a lot of wire wrapping, it occurred to me that what I really could do is, rather than forcing all memory operations to go through register 0, I could make the data register, and that's deceptive because it's not, they're all address and data registers. This is not like a 68,000 where you have different functions. This is a PDP-11. Any register can be used for an address or a data. But the register on the D bus is how you should read data reg or DREG. The register output on the D bus is specified by 3 bits of the instruction word, and the address, the A and B now are specified simultaneously with the A reg field, three other bits of the instruction word. I have not yet tested this or implemented it. I haven't done the hardware, certainly. I was going to do this as a printed circuit board, but never got around to it. And I'm going to implement this with the simulator as soon as I get the simulator for the original version working. This actually can save a few instructions. I've coded a few primitives, and this can save a few instructions. So this is going to be the PISC 1A. I don't think it merits a 2 yet. So that is the quick rundown of the pathetic instruction set computer and how it works. Are there any questions?
I have one. I noticed you got 2 separate bits for read and write. What happens if you set both of them? Will you create a short on the bus?
You won't create a short, but I don't know how the memory chip would respond to that if you try to do read and write simultaneously. Oh no, you might create a short on the data bus because no, that's one output, one input. I'd have to think about that actually. If you do memory read and memory write, I'll have to look at the circuit diagram, but I think there might be a short here, not in the memory chip, but here. I think the buffer will try to drive the data bus at the same time as the register file is trying to drive the data bus. Probably a short.
It may be worth having 1 bit for enable, memory enable, another bit for read or write to be a bit safer.
Yeah, that's the problem. That's that 17th bit that I wanted to avoid using.
No, you use the 2 bits. So instead of memory read and memory write, the bit 15 is enable, memory enable, and bit 14 is, if it's 1, it's reading, if it's 0, it's writing, or vice versa.
So you've implemented your own halt and catch fire function.
So you can have your tri-state then. You can either read or write, or you can have memory at all.
That makes sense.
Yeah, the register file. The register file and the buffer can both be tri-stated. And the question here is it worth adding logic to prevent that from happening? And maybe it is. We actually have 4 signals on the board. There's memory read, which goes to the memory, memory write, which goes to the memory. Read enable C, which is to enable that output on the register file, and write enable C, which means that when data is available on the data bus, that at the end of the cycle, that will get written into the C register.
If it's possible to do a short, so as soon as your program crashes, you might be executing the code that isn't real code. You don't want your machine going up in smoke.
Yeah.
Yeah, that's a very good point, and I should tell you, I should design another safety element into that. Yeah, that's a very good point. As long as I'm designing, as long as I'm revising the design, I might as well do that too.
Only for brave programmers.
There was somebody else there.
Yeah, Brad, had you thought about having an FPGA implementation of this?
I have since. In 1993, I wasn't thinking that way. I was doing well to have wire wrap. But every time I look at this and say I should do this in FPGA, I think, why? Because I can do much more with the FPGA than I'm doing here. This was an exercise in how much can I do with the smallest number of 7400 series chips.
Yep.
And I believe the total chip count is 22. So that was one of the goals. And again, I was a college student. I didn't have the ability to, I didn't have the money to do FPGA. I know it's very expensive now. It's very expensive now, but
today.
Sorry?
I kind of want to try it on this now. See if I can do it with FPGA.
Oh. Yeah.
Yeah, I mean, there is some advantage of low gate count CPUs, even on FPGAs. You know, we've got specialist, you can use them as sort of specialist processors. Obviously, a lot of the big FPGAs have got, you know, you can fit on a massive number of gates, but it's sometimes an advantage to have a very small processor, general purpose processor, implementing a few gates on a FPGA. So there is effort still to have reduced gate count general purpose processors.
I've got a computer here that actually is implementing TTL logic, and it's very, very simple CPU, and it runs code that emulates a more advanced CPU. So it runs more advanced software through it, almost emulation, which is an interesting approach.
By the way, I think it was John Ribel who, at the very same Silomar conference, the formal conference that used to be held every year out in California, at the very same conference where I presented this, he presented his machine, which was remarkably similar, except he did it with an FPGA. And he didn't have some of the ridiculous restrictions that I've required, such as no conditional jump instruction.
I see.
But he got the gate count down to it was on the order of 2,000 gates, which is what this is. This is also on the order of 2,000 gates. I guess I should unsave this and go back to video, which is done.
Well, how does it make?
How do I stop sharing? Oh, there it is.
I really enjoyed that talk. That was
With any luck,
as someone who's trying to design my own CPU.
Oh, thanks.
On an FPGA, I found that really fascinating. The simplicity of it. It felt really, really elegant.
Yep.
I enjoyed hearing that. Thank you.
I also spent many university days designing 16-bit simple RISC CPUs. It was a fun occupation. Didn't do anything for my studies, of course, but.
Are there any other questions to Brad?
Well, I just have two.
Go ahead.
I'm not sure how the PISC would make decisions. How would you do something or something else? And the second question is, how fast can you clock it?
The clock rate is limited to 5 megahertz, I believe, if I recall correctly. Yes, I have a 10 megahertz oscillator and I divide it by 2. You make decisions in conditional branches as follows. There is a way using just arithmetic instructions to propagate the carry bit through the entire register. It's basically a function which is 0 minus the carry bit. I think actually the function is 0 plus 1, or excuse me, register, never mind. 0 minus the carry bit is the ultimate output of that. So you can, from the carry bit, looking at the carry bit input, you can turn it into all 0, the register into all zeros or all ones, depending on the status coming in. And then you AND that with the branch offset, a relative offset. So now you've got either 0 or a relative branch offset, and you add that to the program counter. So with 3 different arithmetic and logical instructions, I can do a conditional branch.
Right.
Fortunately, it has to be relative addressing, but yeah, a lot of systems.
It reminds me,
either genius
Does
or
that answer the
demonic.
question?
it reminds me of that compiler that only outputs move instructions.
Yeah, you can do similar things doing absolute addresses. That works.
It can be done with absolute addresses, yes. It's just a trifle more complicated.
You could read an absolute address from memory anyway, so that's exactly how the ARM does it. When you read, you can read. If you're trying to fit an address in an instruction, you can. So you have to do relative, and the relative points to another address which holds the actual full 32-bit address. See.
Oh yes, I've actually seen that in the code I sometimes generate for the ARM.
Right.
Hi, Brad. When I came across the PISC online, I was very impressed, with the beautiful simplicity of it. And I'm a machine using AMD 29705s along the similar principle. I've actually got here, I've just dug it out beforehand, a tube with 8 74172s 1977 date codes on them. This is a piece of unobtainium here, quite a number of years ago. Ones that someone else sold me. It's a long-standing project I've never got round to doing, but I was thinking of making something with this real chip. I think I'd have to test these chips first before investing too much time in it. But it's a rare chip. When you look in adverts in old magazines at the list of TTL devices, it always used to be the most expensive one. And it must be one of the rarest, I think.
They are rare.
Sure.
I have no idea what. I've sometimes suspected that chip was designed to build the PDP-11, but they are very rare. I get queries with some regularity about, I want to build this, but where do I find the 70? Design to use a different register file chip. And you mentioned the AMD 2900 series. I don't know how available those are. I have a tube full of those. You have a tube of 74-172s. I have a tube full of the AMD parts, which I was thinking someday I would use for a different microcoded computer, but that's one of those never got around to it projects. I think this one's going to require Peter's going to be happy to hear this. This is going to require a follow-up report. I have to get this working. I have to get the simulator working. I have to get the 1A modifications made. And then I have to start, and then I have to get the simulator working. So come back and talk about that. And I have to start looking at the different chips for the register file. So, Peter, you're going to have to schedule a follow-up with me in a year or so.
Very good.
Seems to be about the speed I'm moving.
Very
Absolutely. Good. Yes. We love it, Brad. And you see, with each of our demos, we call these demos a short presentation. We generate a lot of enthusiasm in the FOSS community all over the world. We have people talking from Canada like Brad, and we have George in Japan, and we have people everywhere that want to learn new stuff. We have young programmers also in the group today. And Virgil is the next one with the DUSKOS, which may be related to this kind of developments also.
Right, which means the stage is yours, Virgil. And you can share your screen and give your talk if you want to.
Yes, hello. So I can't share my screen at the same time as I have a video because Zoom is killing my machine. But I'll begin speaking. So yeah, I'd like to tell you about Dusk today, DUSKOS, which is its primary design goal is to be useful for purpose yet unknown. And the goal is for it to be entirely grokkable, understandable by a single person. And another design goal on top of it is to be able to view and print, document, and images. The idea being that important information might sit on different file systems and mass storage devices that are vital to access. So that's the goal of Dusk, and this second design goal widens the scope a lot for Forth, and I didn't want to re-implement, for example, a PDF reader in Forth. It's too much work, and I preferred to go the way of implementing a C compiler, which would allow me to port existing application from the Unix world into a saner world, which is Dusk's world. And so, without further ado, I'll show it to you. So I will stop sharing. I will stop video, and I'll share my screen here. Here. So yeah. So this is my terminal. I'll stay on it for just a few seconds because the idea is what to do with a fresh. So do you all see it?
No, it's all a black screen by me. For me.
Do you see it now?
No, no.
I see it, terminus.
No, okay.
It's a black screen, but the prompt is in the upper left.
Yeah,
Oh, okay. So you see the prompt.
terminal.
So you see it. Do you see this? Do you see DUSKOS?
I do. I do.
Yes.
All right. So anyway, I'll share a QEMU screen in a few minutes. This is just to say that from a fresh clone of DUSKOS source code, you just need a C compiler and a make, and then you do make run, and it behaves like a regular Forth would behave. But so what I wanted to tell you is that this is not what I'm going to show you because one of Dusk's primary attributes is that it's an STC that plays a lot with code generation, and for this to be interesting, we need to be in i386. So what I'm going to do, so you need QEMU for this, but you can, so you run make PC run, and then you get a QEMU emulator. So this is very slow, but this is Zoom killing my machine. I don't understand. So I'll stop sharing, and then I'll share my other screen. All right. Now, normally you should see something that is pretty legible. So everyone can see the text correctly. It's not too small. All right.
Mm-hmm. Yeah, I also see.
So this is. All right. So this is a DUSKOS running on the i386 in the QEMU emulator. So so this runs on bare metal. There's nothing underneath this. So what I was saying is that why i386 is because Dusk is an STC subthreaded code. So it's its execution model rather than ITC or DTC. Because why did I choose STC is because because I have a C compiler, I want Forth definitions and native definition to intertwine freely, which isn't impossible in DTC, but it's complicated. Whereas in STC, it's natural. You just call any word, and when you return into whatever the hardware stack tells you to return. So I'd like to show you how it piggybacks on STC. But before that, I'll load a disassembler. So i386D. Yeah. So this is a disassembler. Dusk has a file system rather than blocks, and it's not out of personal preferences. I prefer the traditional way of Forth and with regard to mass storage. But since I had by design to add file system complexity to Dusk, I figured why not piggyback on it. So file systems is at the core of DUSKOS. So this is what I'm loading. And then let's define just any word. And it behaves as expected. So what's interesting here is when we disassemble this. So in a naive Forth, we'd expect this disassembly to look like something like a call to a literal word, which then pops, which then reads the PF and with a 3 in it, and then calls plus, and then calls dot, and then returns. But here we see that there's a lot of code that has been inlined as i386. And sorry for those who aren't familiar with i386 code. I require it to make my demo. So this is i386. So what we see here, you see my mouse pointer. So what we see here is a dupe. So oh yeah, I forgot. So there are 3 registers that are used in the i386 port of Dusk. ESI is for PSP, ESP is for RSP, and all Dusk ports have top of stack register, and in i386 it's EAX. So these are the 3 registers that we play with here. So what we see here is that we grow PSP in the first line. We grow PSP by 4 by adding -4 here, and then we move top of stack to second top of stack here. So these 2 lines are a dupe, and then followed by a move of our immediate into top of stack. So these 3 lines are the equivalent of a literal lit n. So that's how 3 is compiled, and then there's the plus, which is one of the inlines word of Dusk. So plus can be called just fine like this, but when it's compiled, rather than compiling a call to it, it compiles native code. So this is what we see here with add EAX ESI. So it adds the value of second top of stack into top of stack, and then it shrinks PS by 4. So this is plus that has been inlined, and then there's a call to dot, and we return. So so this is how Dusk piggybacks on STC. Any questions so far? No, I'll continue. So I also wanted to tell you about immediate mechanics. So in Dusk, so here we have all right. So this is a regular immediate word. We know how it behaves. It's like any immediate word in any fort. Now in some forts, we want to have behavior that depends on whether we're compiling or not. So in many forts, we'd see something like this. Oops, sorry. Compiling if, and then compile else run. So this is something you'd see in many other forts, but this doesn't work in Dusk, because in Dusk there's a special mechanism for this behavior selection, and it's I'm going to show you. A fort, a word is always runtime by default, and then so this is a regular word that prints run, and then I use the word compiling as a special fragment grafter. I come and graft a piece of code to the current code. So here I have compile. So this makes my word immediate, and it does as you'd expect. So foo or bar foo. So this is how we get dual behavior. Why did I do this? Because the traditional way is fine, but there are few places where the behavior selection happens at the wrong time, because behavior selection here happens at runtime all the time. You know, if you compile it with compile here, if you compile foo like this in another word, and then you can't have a precise selection of the behavior at compile time. So, and this becomes very important when we get into the subject of inlined word, such as the plus that I've shown you there, because it introduces, the traditional way introduces very tricky bugs. So this is why I went with this system. So to show this this mechanism to you, I will recreate the word nip. So let's say that we have no. First of all, so we create the first step is to create a nip compiler. So nip comma, and then I use here the HAL. So I can't tell you about the HAL now because it's too wide of a subject, but let's just say that 4PS plus here is the equivalent of shrinking PS by 4, which is what we do in nip when we're in a fort that does that has a top of stack register. So this is my nip compiler, and then I create the word nip, in which I compile nip and then exit. So this works like you'd expect. For example, if I nip here, I'm nipping 2, so I get 3 and 1 because I've nipped 2. So it also, of course, works if we compile it. So 1, 2, 3, dot, dot. So we get what is expected, and then if we disassemble this, we will see that, as with a regular word, this nip nip is called, which is sad because, well, we can inline the single and I3D6 instruction, so it's a loss. So instead, what we'll do is that we'll make the nip word inlineable, which with my little magic word compiling. So here we see that with code nip, I run nip, and then I run the nip compiler and run the exit compiler, and then with compiling, I compile the nip compiler and then exit. So this nip is now inlineable. It works at runtime. It works exactly like you'd expect, and at compile time, it does its thing. So the foo word will work, and if we disassemble it, we see that instead of calling nip, it inlines the behavior of nip. So that's immediate mechanics in Dusk. Any questions so far? Am I going too fast?
Yes. What are those extra instruction of the return call?
This is just memory. My disassembler disassembled 15 lines by default. So this is just memory. After the return call, it's bad memory. It can be ignored. All right. So I'll continue. So this was immediate mechanics. So this is a small stepping stone towards the C compiler. I won't have the time to tell you about the C compiler because I don't want to take the time of other presenters. But what I want to show you are the stepping stones leading to it. So this little bit about compiling and inline compiling is a very important stepping stone toward greater things. Now I'd like to tell you about two semantics in Dusk. So we all know about create. All right, so this is a regular cell, and then we all know that we can read from it and write from it and so on. So Dusk, like many other forts, has what we call values. So values are like cells, but they are automatically dereferenced. So we can access the value directly without having to fetch it. And like with many other forts, we use the to word to set the value to it. So to my val, then my val that you get the drift. Now, what is special in Dusk is that Dusk has a widened selection of two words. For example, there's 2+. If I use 2+ on my val, then it increases my val by 2. So we have 56. and there's a whole selection of two words, and an interesting one is, for example, to fetch plus. So, for example, if I create an array here, all right, and then I create a pointer to that array in a value. All right, so you get the drift. This is data is an array. Pointer is a pointer to data. So we can dereference pointer. We get the first element of the array. So if I use to@fetch plus pointer, what it does is that it dereferences the pointer and increases it. So to@plus ptr dot, we get 54 and so on. Now, so this is interesting, but now the really nice part where stepping stones play together in a very interesting way is if we compile this to ptr. Now, what do you think happens when I do that? Well, first of all, it behaves as expected. And if we disassemble it, then we will see that things are really crazy on the code generation side. Because, so in a naive Forth, you would get something like a call that brings the address of PTR into PS, and then PS would get consumed by the read of it, and then the increase of it and stuff like that. But Dusk goes to crazy levels to generate efficient code for it. So what we see here is a dupe to accommodate the result of our 2PTR, because 2@fetch results in as a stack signature of adding a number to the stack. So this is so these two lines are the dupe, and then this is a direct. So this is a native i386 instructions that moves the hard-coded address of PTR's cell into EAX, and then the other instructions which hard codes the address memory by 4, and then it does the end direction. So this is one of the big feature of Dusk, and I don't know if other forks do that, but anyway, I'm really proud about that. So this is it. Now, why do I call this to semantics rather than value semantics? Good question. This is because two words apply to more than values. It also applies to local variables and fields. Fields, I can't talk to it. I can't talk about it now. I'll talk about it in another session, but I can show you local variables, which work, I believe, like any other local variables in other forts, except that it doesn't do naming. The names are hard-coded. It's V1, V2, V3, V4, and they refer to slots in the return stack. So, for example, if I take foo, which takes a value from PS and pushes it to the return stack, I can use, for example, 2 plus V1, and then pop that back. So this applies to semantics to an RS relative address. So, for example, 54 foo will yield 55, and then if we disassemble it, we will see some crazy stuff. So we see that the first two lines are the push to R. LODS is just a fancy optimization because of the register usage. Because of the register I use, it just so happens that I can use LODS rather than a more lengthier set of instruction. But so this is push to R, and then as we see, this is an increase of an add an addition of 1, 2, and direct ESP, which is my V1 slot. And then the 2 other lines are the pop from R. And this is pretty much it. This is what I wanted to show you today about DUSKOS. So I don't have the time to cover the rest, but hopefully I've got you hooked on it, and you will be interested to see the other stepping stone leading to a C compiler in Forth. So I will stop my demo and answer questions if there are any. Stop share.
Thank you very much. What a nice talk, and how amazing native code generation.
This is a question. May I try a question?
Sure, Christian.
Virgil, I've been trying to use your DUSKOS, and I got stuck trying to figure out which machine would be best to run on.
Yeah.
So what would be the ideal machine to try it with?
So Forth is ported to a few machines yet. So the first port was a PC of the PIIX architecture. So whatever has, if your machine has a floppy disk controller on it, then it should be golden, except for very old PC that might have compatibility problem. But stuff like, so if it has a floppy and an ATA drive, then it should be all right. But anything more modern becomes more complex, and support for it isn't golden. I'm working on it. Another option is the Raspberry Pi, because there's a Raspberry Pi port to it, and then there's the advantage with the Raspberry Pi that it has a fix, so everyone has the same Raspberry Pi, but support for it is partial. There, I only have the UART that is available through the GPIO pins, but otherwise it works. So if you have a Model 1 RPi, then it's easy to get Dusk running on it. But yeah, otherwise it's a bit complicated to deploy Dusk on real hardware, because there's no auto probing or stuff like that. You have to know your hardware and what?
Now I feel sorry that I threw away 5 of my PCs of the 90s about a month ago.
Yeah, I'm sorry too. I wish you had given them to me.
Anyway, but it's very CPU dependent, so it works on the 386 or similar, like 486, and
yes,
on ARM.
Yes.
No other CPU supported yet. No
Not yet. I'm planning on others. So my next target, I have an old PowerBook here, so I'd like M68K afterwards, but I'm not there yet.
Easy 80 could be 24 bits.
No, so this is a 32-bit Forth. I have CollapseOS, which is for 8-bit and 16-bit computers, and which support more Z80 6502, 6809, which I love. But this is a different project, because CollapseOS is a DTC which has compactness as its first.
Yeah.
As one of its first design goals in Dusk, because we target 32-bit machines which have tons of RAM. The compactness is not a design goal, so I went crazy on code generation and stuff like that, which uses a lot of memory. But for Forth, of course, it uses nothing in terms of memory compared to anything modern. But compactness in Dusk is not a design goal, which allows me to play with code generation a lot.
Yeah, I see. But maybe a 24-bit CPU like the EZ80 in 24-bit mode could be a viable target for it.
For CollapseOS, yes, but not Dusk. I really hard coded 32-bit everywhere in the code.
And for those that haven't kicked the tires, you can also you've got it set up to run with an emulator, so that's always an option if you just want to play with it.
And yeah, of course. So emulators into Dusk and into CollapseOS are primary application targets. So I already have a 6502 emulator in Dusk. So Dusk has a 6502 emulator that it runs CollapseOS on. So you can have a Dusk system that emulates CollapseOS in 6502, for example, for the Apple II port of CollapseOS, running on a i386 bare metal Dusk.
Mm-hmm. Do you think DuskOS can boot from an SD card?
Yes, it can. Yes.
Mm-hmm. Okay. So yeah, because you said floppy disk is required.
Well, it depends on the BIOS. If your BIOS can boot from it, but hardware support for eMMC is not done on the PC yet. So I have eMMC drivers, but only for the Raspberry Pi yet. But you know, I'm all about developing drivers. I'm working on that.
Sure.
But anything with EFI is not working in the PC world now, not natively.
I didn't get that last that question.
Oh yeah, if you have a PC with UEFI instead of BIOS, then it won't work.
No, not yet. No UEFI yet. But I'd like to get this working as well, but I haven't got to it yet.
Okay.
This is Christian again. One more question. You obviously had to do some research to get this done. What was your inspiration as far as other forks are looked at? It's the first one I see that is STC on the 386.
I don't have many inspiration. To me, Forth, it's special how I came about Forth is that so my introduction to it is starting Forth from Lou Brody, and I hadn't tried any Forth before. It's just reading the thing and trying to implement one. Just it really connected with me, and now at that moment I just wanted to realize that vision, and I hadn't any time to look at other forts. I just went with it and done it. So there's no real inspiration. You know, I tried looking at G-Fort and RetroFort, but they don't. I just don't like them. So I just went my own way.
So it's pretty well your own creation.
Yeah,
nice.
Yeah.
The only other thing that I saw that is similar is ColorFort. It boots from the floppy like you can do it. But I don't think it is STC.
Yes, it is.
ColorFort is STC?
I didn't know that. I never look at things deep enough.
All right. There are additional questions to Virgil.
Excellent, Virgil. Fantastic.
So, thank you very much. And we proceed with our next speaker. And we hope to hear updates about DuskOS, of course. I saw glimpsing your homepage. There are a lot of things on the roadmap. So, of course, we're curious about updates. Right. I think we stick more or less to bare metal or, yeah. And when we look at the work that Pablo will talk about, Forth is simple but not easy. So, Pablo, let's see.
I'm here. Thank you. I share the screen. and I start to talk. Well, for is simple but noisy. First, hello world is a terrible idea for comparing language. It's just a call for the operating system that has nothing to do with the way of language define that data and actions. Programming is the task that you want to perform. The language is the tool. Of course, the war between fanatics of different language is useless. Let's now go there. Writing code without thinking about the problem you want to solve make this problem bigger. The phrase, because it's done that way, can complicate the problem to get solved. Generalizing a problem brings more problems too. We humans love complexity, but in the task of programming, this is not convenient. Why the different high-level language? What advantage do you have? It is said it's faster, it's safer, it's more productive. None of this mean anything concrete. Starting from the machine code, we can see that the real basic advantage are: first, don't not using memory address, but through labels. Two, manage memory space using the concept of variable. Three, avoid using jump or goto. It's make reading the code difficult. The famous spaghetti code. Four, use a construct for the flow of execution, conditional, repetition, and recursion, basically. But discontinue. The rest of the features they are added are not to facilitate programming, but have it to do with controlling the programmer or defining a way of programming. For example, when I define in C code 2 bars, an int and pointer to an int, the indication of the variable address is for the programmer, not to confuse them and the compiler to warn him when it's assigned incorrectly. Although in reality both are integer, I can do the same thing with the bot. This control over pointer is intensified in later language. For example, Java say there is no pointer. We call it reference, and the possibility with controls are incredibly restricted. Again, for the programmer. In Rust is an extreme example of this. You need to define the memory size. Use a function as a parameter, and if it is different, it will not compile it at all. Imagine if I decide to change this size in how many places in the code I will have to modify. In Rust, also, the definition if something is called outside is unsafe. I must recognize that the marketing of paranoia is very successful. This is an example of C with this unsafe features. For me, it's a feature, but it's a nightmare. The system of objects is more complex, but the idea is the same, restricting to the programmer the possibilities of combining the part of a system, promising simplification. I understand that it's not advisable to change your mind too much about the implementation. Redoing part of or all of the problem is much more expensive than modifying the existing codes. This cost is associated with the previous restriction. I suspect that the reality is in the other way around. Remaking the system from zero is the only way to make better program, and is often faster than trying to improve bad implementation. System with I will change, and for many reasons. Understanding better the problem, change rules, try another part, etc. Another example is the strings, character strings. Strings is not really a variable, since at the machine code level, it does not fit in a register. String operation array, memory movement, or operation with pointer. You have to choose or pretend that is a variable and hide these two mechanisms as if they were one, or expose reality and work what the difference of what being done. For is simple because they are minimal rules for describing code and data, but it's complex because it exposes and allows you to work with all the behavior of a computer, and therefore require you to know what is really happening. It does not condition the programmer to write rules that limit him. The programmer must realize for himself that he is doing this wrong. The data is organized in memory map. Keep in mind that everything is a number that is used for count or locate. The pointer or address is the most powerful abstraction. Behind the name, we can put a number, a string, a set, an image, a sound, a code, etc. We use a stack to describe the calculation flow of data. It is difficult to master and require practice because with this local variable and parameters become relative position in a stack. The code you see right is only half of the how is work. The other half is the stack image that we must calculate while each word is executed in mind. Hence, it's possible to cut a part of code that don't obey a condition or a repetition or a stack change and factor it immediately. The stack is the only connection between part of the code. For is simple, few rules, few concepts. It is generally true is missing thing, which is difficult to master. Forth is simple, but it's not easy. I have an example too. I translate C code from my system many times, and I develop or I use as a common approach. This is a C version of the interpolate function, and the same interpolate function with the same parameters is showing here. For make this, first I disassemble the formula and rewrite in postfix notation with name of the variable, and then try to position every parameter in stack and reference to this position with do swap pick anyway, and try to make the same calculation, but the comment are in my mind, and it's not part of the code. With this result, I can factorize, for example, slope of the line. Simply copy and paste this fragment of code and make other word and reuse. And when analyze this code, I try to simplify and make things like what happened if a slope is give me with the division resolver, and try to see what is the better order of the stack for simplify the word, and I can go to see with the new discover or new try of the problem and see what happened. This is one. This is make me think. For is really it's more a language. It's a form of thinking about the problem. I program in JavaScript and in PHP for work, and use these principles for making program. Try to maintain, try to keep it simple, and try to modify another things for simplify the system. This is all. Thank you. Any question?
Yeah, François here. I think
Thank you.
that you should document your stack effects in your code. You really should. Otherwise, it's impossible to maintain. So the comments are really part of the code, even if they're not executable. If you don't have them, it's not going to age well.
Something not make a comment, make you code protected by obscurity, and in for is very.
Well, if you
very common.
You intend to maintain your code in the future, even in a month or two, and you have no comments, it won't work. You will have to
yes, but
first, and then you can change it.
Yes, but you you not write the stack every word you write, because the code be the double of code, but for the comment of the stack, not comment the stack, but comment about generality of the code.
I do both, but I document stack effects as well, and it's a significant part of my code, usually. When it's simple, no, I don't document stack effects. But when I'm like you do, if I have to handle 5 or 6 levels deep, yeah, it is documented for sure.
Okay.
Pablo, do you ever
Yes.
find yourself solving a problem in Forth and then using that strategy for your work program language?
I don't understand the question, Peter.
In other words, if you have something you need to program at work, do you stop and think about how you would program it in Forth first, and then use that to formulate how you do it in your other language that you need for work?
No. It's the general idea of Forth influenced me to other language. This is the what happened with me.
That's what you said. You approach Forth as a way of thinking about the problem and structuring your code. That's what you said. You said you did that in JavaScript and PHP.
Peter, help me with the significance of the question.
I will speak in Spanish for Pablo. Pablo, está bien, vos estás respondiendo lo mismo que él te pregunta, así que está correcto. It's correct what John asked to Pablo, and Pablo answered this. Yes, he is using force thinking, and then he develops in JavaScript or in other languages. It's okay.
A ver, sorry for the Spanish. Peter, a ver cómo podés traducir esto. Pensar en for lleva principalmente a no estar atado a ningún tipo de convención que te imponga el lenguaje.
Pablo is saying in force, when he thinks in force, there are no conventions that happen in other languages. So I think he's saying he feels more free. Because force has no typing, it's no typing, and this is my opinion, no? And force has no restrictions like other languages have. So I agree with Pablo in that sense.
It's more difficult, more free. This is the resume.
I actually find the Forth in interpreter a very useful piece of code. For example, I've written a Z84 for the ZX Spectrum Next, where I use BC as my top of stack, and I use that approach. But just having the 3 routines, I'm able to embed almost like an interpreter into any kind of application. So, for example, if I'm writing a text adventure game and I want my logic of a text adventure game to be written as kind of like data, I can do that in kind of a Forth style language, where I can support just really basic primitives and then build everything up on top of that. And the actual code to actually run that and get me started with something very simple is just several bytes. It's really powerful, and I was able to get one up and running just for just in a matter of about half an hour, just messing around. That's when I feel real power.
I feel in my case, it would be very difficult for me to go from Force to JavaScript because of the freedom of Force, and you write a shorter code, more factorized code. So in my case, it would not be possible to think in Force and then write JavaScript. I could think in Force and write assembly, but not a higher level language.
I write JavaScript code very much, and I try to maintain in basic form of JavaScript and build over top. And I try to not using frameworks because this complicate the solution. If made for a certain type of application and complicate the others. And if you stay low in the language, the basic, you go with less error and more fast. This is my opinion.
I saw many times, we have many programmers of C language in the Force community, and writing in C and in Force is very similar. They can, in that way, they can think in Force and write C code. There is no problem. I do this also. But for example, if you use C++, then you enter into trouble, because the higher you go, Force is at another level, and this makes difficult to use Force thinking in that at that level, at that higher level. That's my experience.
This is Christian. I have very little experience with any other programming language. Fort and Assembler are essentially my only languages that I have experience with. And when I use Fort, and when I start to get confused, if I want to create something too big that exists in a higher level language, but does not exist in Fort, I end up having to create too many things and I give up most of the time. But if I create smaller things that allow me to create the bigger thing, then I end up being able to get through the task. So I think the whole secret with Fort is really dividing things in very smaller chunks that you could put together to end up with something that is very similar to what's being done in the higher language. But it's a lot of work to do all those little chunks. That's where sometimes I get a bit exasperated. I give up for a while and I come back a week after. much more work in Fort, but you understand clearly what you do. And higher level languages, something did it for you, but you're not too sure what it did. But it seems to work. So I like Fort for being in control, but it makes me sweat a bit.
Well, yeah, I'd like to piggyback on that. This is interesting because this is also my opinion, is that the genius of Fort is that the path of least resistance goes toward what Alvaro said is a key word, is composition. And composition is key in Fort. You know, if you try to build complexity through linear abstraction, then you go too high too fast. Abstraction will eat your complexity budget and you're done. Whereas if you go the composition way, then you stay flat, but it requires a lot more work to do so. You need to think real hard about how the pieces of complexity will work together, compose it with composition, and then but other languages makes you go too fast, whereas Forth, it forces you to stop and think, because the high stack of complexity is harder in Forth, so it forces you to stay flat. So yeah, that was my two.
Forth does have its weaknesses, though. Forth doesn't handle complex data as well as other languages. Like if I'm dealing with complex structures and references and stuff, I'd rather use a language like Rust over Forth anytime. But if I'm writing low-level stuff and I want to interface hardware, like Forth is amazing. Like I might even consider doing video games in Forth too, because the data structures tend to be a lot simpler. But if I'm doing anything really complex, like I don't know, some sort of server backend, or which has to deal with data from various users and so forth, and it is a struggle, at least with traditional Forth. It's definitely possible to come up with words that help with more complex data, but Forth out of the box doesn't really help that much in my experience. So it depends what you want to do. I don't think traditional Forth is the be all and end all of languages. You can make it great by creating the DSL that you want to do your application, but it takes effort. Where some other languages, like even JavaScript, it can handle data structures like hash sets and things like that a lot better than Forth can.
Excellent, excellent. Any other questions to Pablo? If you all agree, we continue then with the schedule. And the next participant is Rob Probin with music, robot music.
So I'm also aware that myself and Ulrich are between us and coffee, so I'll try not to take too much time. So I'm not a musical guy myself. I listen to a lot of music. My kids and my wife's more musical, but I often get distracted, and Forth is one of my distractions, I guess, and robots as well. So I just thought I'd share a little bit of a bit of a distraction I had with the robots. So let me just share my screen. Share that. So you've seen this robot before. This one. Can everybody see that?
Oh yes.
Yeah. So this is one of my robots. It's the UK Mars bots. This is a sort of standard design robot that I helped with to design it. And so let me just show you what it normally looks like. So normally it looks like this. So this is a sort of stock robot. It's got an LED down the bottom. It's got motor driver, motors, and then this is an Arduino Nano, which you could program with FlashForth, for instance, would be one of the options. There's a few options. FlashForth I've used on it. My version of the robot, if I go back to this camera view, has got this Arduino Nano. So this is a Raspberry Pi based, a Raspberry Pi Pico based RP2040 micro on it. It's got Wi-Fi on as well, although I've got this HCO5, HCO6 Bluetooth module, serial Bluetooth module to talk to it. And the LED, what I want to point out is this LED is actually replaced by a piezo buzzer, right? It's tricky when these robots move more than slowly. It's tricky to know what they're going to do. So you can obviously log data, and you can have commands to get it to do particular things, particular Forth commands. But having a bit of audio feedback, just a beep, I find quite useful. You know, you can perhaps more easily see when it's going to start a turn, for instance. So originally I had instead of the LED, I put a self-oscillating buzzer on this. But obviously, I can't leave things alone, right? And so I swapped this for a not self-oscillating standard piezo buzzer. And then, of course, well, this Raspberry Pi, this RP2040 has got a PWM circuit on. So if I go to the data sheet, there's a PWM. It's actually got 8 PWM units, and they've all got two compare. So anybody who's dealt with a PWM is fairly familiar. PWMs can be configured several ways, but one of the ways is they count up and then they change state when they reach the compare value, right? So when you want to produce sounds out of this using a slightly different way. So PWM on the motor control, and this robot's uses PWM for the motors to control the effectively the voltage into the motors. And that uses PWM units as well. I won't show you that code today. With that, you're just altering the mark to space ratio, right? So you're altering the amount of time it's on, and usually got a fixed frequency. And normally you set that as a frequency above human hearing, because they tend to whine a little bit. Although it's not uncommon to have robots with 4 kilohertz or 8 kilohertz PWM, but these are set significantly higher. But for making tones, obviously you want your cycle time to be set at the frequency you want to listen to, and then maybe you set the volume to be, we set the mark space ratio to be 50-50 to get the maximum volume out. So the first diversion I had, there's another chip on this. There's another chip that's got this Arduino Nano form factor, as well as the Arduino, as well as this RP2040 Connect that I'm using. There's a cheaper micro which some of my other robot colleagues in UK Mars are doing, which is this Maker Nano. And what I've got a couple of these as well. I seem to, as several of us probably on the call do, I tend to gather these, whether I can use them or not, it's a different matter. They actually supply an example project, and this is what got me producing music initially. And it's in Circuit Python, which is a variant of MicroPython, and it's okay, but I've got a bit, as all of us on this call, I've got a bit of an itch regarding Forth. So there's a data table which plays at some sort of simple melody. It flashes some LEDs as well, and it uses this pre-existing library, which I'm obviously not interested in at all, right? So as somebody was saying, sometimes you have to build Christy, I think, was saying you have to build your own tools up, but that's okay. That sounds like fun to me. So this is the Forth code. So I'm running Zepto Forth on this unit. So let me have a look. So this is creating these tables, right? Exactly the same way as they're done. In fact, I think I might have even just copy and pasted the Circuit Python code and changed it to Forth. Put a constant with the number of notes. So this is the way I started it. So then you have to figure out how to use this PWM unit. And what you end up doing, if I go back to the diagram, is you've got to find the fractional and the integer part of the counter, right, to match this frequency. So I've got plenty of comments in here. So Zepto Forth has got fixed point numbers. It's a 31-bit integer and a 32-bit fractional part. So this is pre-built into Zepto Forth. So that's saved me creating my own floating point library. And effectively, this function or this word calculates the closest dividers with a loop. Now, we were talking a bit about Forth factorization before my talk, and I generally find that once you've got a whole bunch of depth on the stack, you really need to refactor. And this actually went through a couple of this is probably the most complicated word I really want to write in Forth, right? And it's probably affecting my coding in C and C++ and in Python. Effectively here, what we're doing is this sort of complicated equation, right? But we need to sort of iterate round in order to find the highest, because we want the highest number that to we've got the most accuracy in the timer. So we loop round, and I could go into detail in this, but I won't. The key thing is that when I wrote the first pass, it was significantly longer and more complicated, and I went through sort of a short iteration to try to find a function that I could understand quickly. And then I also created one to go the opposite way, right? So here we put in the frequency in hertz, and it produces these three. I've also got the opposite way, which effectively prints, which validates my what's it called. And in fact, why don't I just, to make this practical, let's take, and I'm not usually expecting to type these sort of things in. Let me just get rid of this. How do I get rid of? Never mind. I'll do it right. Let me just move this around a bit, rather than figure out Zoom's user interface. How annoying. Annoying. Right, so let me just put in here. So let me assume I've got 1,000 hertz, right? So I'm not sure why this isn't rescaling. Actually, let me just reload this. Aha, it's better. Right, so I want 1,000 hertz. Let me connect back to the robot. Kind of reloaded this is Travis's terminal, which runs in Chrome, which I've been using recently. So if I put .s, you can see that it's calculated, and maybe I should have started with an empty stack. So it's calculated these values, right? And if we go back to the source code, it's fractional divider, integer divider, and top count. So the top count is just below. So the register, this registers a 16-bit count up register, right? So we want that closest to 65535 that we can get. And the integer divider is 2. And there's no fractional divider. And if I use the opposite function, print actual frequency, so it's bang on. So this, for that frequency of 1,000, and the clock rate for the system clock rate is 125 meg on the RP2040. So when I turn a tone on, right? We do some manipulation of the PWM. We disable the PWM. We reset the PWM counter, calculate the closest dividers, load those into the PWM registers, set it to free running mode, turn off the phase correct. The phase correct on PWM is where you go, where it counts up and counts down. We don't use that on the robot. And then we enable the PWM pin. So if I take this and put, I don't know, 2,000, which should be a sufficiently annoying tone. Can everybody hear that? Don't you love piezo buzzers, right? So turn that tone off. So this is sort of how I built up. Then I added another tone, which allows the duration and frequency. Then I wanted something which this is just a word, a custom word that indexes into this duration and melody to the two arrays and fetches the correct one and calls tone on it. And then we've got a function called Mario test. That rather gives away what the tune is, but that tune on the demo project is like this. I don't know if you can you hear that? It's quite quiet because this piezo has got a best resonating frequency at 4 kilohertz. So if I move this over here, I guess you can hear that perhaps. So then you've got, this is all standard stuff. Sound up and sound down. And then what I did was couldn't leave it there either. So there's a notation called ABC notation, right? And it basically has got a way of writing music in text format. And there's a whole bunch of rules. I haven't got all the rules coded up, but I got a bunch of them. And if we scroll down to the bottom of this file, this is the music for a Sinclair Spectrum game called Jet Set Willy. Although as you'll hear in a minute, it's not. You probably recognise it as Andrew Lloyd Webber's copyright. So this runs through this string, getting each note, GF. So these are the bar markers, GF. This means that the duration is 2. So this means that it's a lower octave. So if I play that, can you all hear that?
I can't hear anything. I don't think your mic is picking up any of the music that you've been playing so far.
Right. Okay. Let me just move this closer.
A lot of mics do that. They cut off background
noise cancelling. Yeah.
Right. So, okay. Right. Well, I'll have to record a web and post it on the Facebook group anyway. So going back to the fourth code, I'll make a web recording and post it to the Facebook group so you can hear the tunes. So this is actually going through, basically doing a string parsing of this string. So it takes get note here, runs through get note and make note. So get note, new note just initializes some stuff, checks for bar lines. So it runs through the string getting the bar lines, passes the guitar codes, fiddle bowing, so accents and accidentals. You have a look at the top of here. These are the accidentals, which are to do with the which octave that note's on. And then where was I? Right. So then it reads the bass note. And if it hasn't got a bass note, if there's an error in the string, it aborts. Then it gets a note length. So octave effectively merges these accidentals and bass notes. Note length reads the note length. Finish number effectively amalgamates. You can have it's more complicated than a single number. So finish number effectively amalgamates that. And then this converts it to a frequency. So you end up with either false if there's been an encoding error, or true with the duration of frequency. And then at the back of that, it does make note. A make note effectively turns the tone on for the particular duration. So I've just got an milliseconds wait. So it goes note length of milliseconds and then milliseconds and then turns the tone off. And it just loops around this. So that was that. I also coded up some of Peter Jacketty's things from his MA-Crisp extensions, the tachyon extensions for MA-Crisp. I put some of those in as well. Seeing it's not picking up the piezo buzzer, I'll just record those on the video and post it. So that was it. I don't know whether anybody got any questions.
Excellent, Rob. Fantastic.
I'll post a
no questions.
I'll post a link to the code as well, just in case anybody wants to play with it. It should be. It's relatively standard Forth, I think. Septo Forth is pretty close to being standard Forth.
Excellent. Thank you so much, Rob.
Mm-hmm. Thank you.
So the next participant, Ulrich Hoffmann, will show us a tutorial about forced data structures. Thank you, Ulrich.
Yeah, let me see. So that was not the right thing. I would like to share the entire screen because we will have a demo as well. So yeah, hello everyone. Yeah, I hear voices that Forth doesn't support data structures. It's up
You're
to
going to prove
us.
me wrong now, aren't you? You just going to embarrass me.
Yeah. Anyway, we have a look at this. This is classical structs or records, and we will look into how Forth actually does this. So we will start looking into variable and value definitions and the difference about that. You probably all know about this, but this puts us into context of what structures and what value flavored structures are. And then we will have a look at, well, my take on that. And I must say we're in a long-term process in standardizing these. So yes, they will be built into Forth eventually. And for the time being, it will be a library that you can load on a standard system and then make use of the value flavored structures. So we will have a look at my syntax and how you would use it, and look at some concrete examples when we do a short demo, how to use them with GForce. And then I have some words on memory access operators, which is another topic that is due to standardization. Like how do you portably access 16-bit values, signed and unsigned, 8-bit values, 32-bit values, 64-bit values. You can't just use fetch and store because that depends on the Forth system that you actually have, whether you have a 32 or 64-bit or 16-bit system, then the fetch and store will have different widths. But if you want to explicitly have a 16-bit fetch, even on a 32-bit system, then you have to do something else. And so there's ongoing discussion how to do that. And then we come to some conclusion. So let's talk about variables and values. The main difference is they name a cell in memory, and the main difference is that you access them in a different way. Variables are accessed by store, to store a value in that exclamation mark, and fetch to get a value and put it on the stack. And values are accessed in a different way. So you write to them using to and plus to increment. And if you name a value, then its value is read implicitly and put on the stack. So you probably all know about that. So you can write something like variable amount, and then you can store 55 in that, and you can fetch the value. Or you can have a value, and the typical definition of value requires you to supply an initial value. Then you can use the to notation to put this in. And yeah, so you avoid lots of fetches if you read the values. And well, maybe more important, there could also be other value-like things like double values or floating point values, and you can use the same to notation for this, and the value would know what type it is and do whatever is necessary. And if you name the value, then it will put the appropriate content on the stack. So if you have maybe IO values that read ports, you would just name it and it will read the port and put the value on the stack. So that's some kind of abstraction. You don't need to remember what operators to use. And on the variable side, you do need to remember this. You need to do a port fetch, or if it's not a memory mapped IO port, or you need to do an F fetch if it's a floating point value. So there's some value in using values, no pun intended, but variable is the more basic way to do it. Okay, in standard forth, we already have records, and I talked about that in an earlier talk. So you can define something with begin structure, end structure. You can give the structure a name, like point in this example, and then you can specify fields, and fields can have different memory width. You can say how large the field actually is, and you give the field a name, and the name will actually do the appropriate address calculation. So if you did this, then point will be a constant-like thing that puts the size of the defined structure on the stack. And then you can say something like create p, which creates a new variable like thing with non-allocated memory. And then you say point a lot to allocate as much memory that is necessary for a point data structure. Yeah, and then you can use the field names to do the address calculation. You say py to get the address of the y field in the p data structure. And so you can write 55 py store to store the values in there, and you can say py fetch to get the appropriate value. So they are like variables. And if you have a floating point field, you have to use ffetch to do that. So the begin structure, end structure is just syntactic sugar. So you can also write it like you see it on the right side. Put the 0 offset on the stack at the beginning of the definition, and then the field does an appropriate offset calculation at compile time, and which in the end results in the size of the structure that you define. So begin structure, end structure, just syntactic sugar. And so let's see how this works. I have on the left the code again, and there's the red bullet that says where we are about to execute. So we assume that the field y is already initialized with 55. And now we want to execute p, which of course, as it's a variable-like thing, puts the address of p on the stack. Then we want to execute y, which is a field, and it knows about its offset relative to any structure that is a point structure. And it assumes to have the base address of the structure on the stack, and it does the appropriate address calculation. Yeah, and so if we do that, then it does a +4 in our case, 32-bit system. So now we have the address of y on the stack, and we can do the fetch to actually get the value 55, and then we can print it, of course, or do whatever we want with this. So you have to do the memory access by your own. You have to remember the width of the field to actually access it in a correct way. Yeah, right. And that causes a lot of problems, especially if you move from 32-bit to 64-bit systems, because then fetch and store is suddenly something different, and you have to remember all the cases where, oh, this is really a 32-bit value, I want to fetch it, and so on, especially if you interface with C libraries or other external data that is supplied. So that brings us to the idea of value flavored structures, and you get the idea maybe from my preparation about variables and values. We want to have value type fields, so it's not just the size of a field, but also the appropriate operations that you want to do on that. And why should the programmer keep track of all this? So he has to remember when the structure changes, or when you port it to something else, yeah, the hardware property changes or whatever. Let the compiler do this. And so we really want to have things that are like values that know about their size and their access operators, their reader and their writer operation, or the increment operation. And that's the idea behind that. So we know limits, values we do like this. We saw this earlier. And now we want to do something like, yeah, instead of field, we say value field. And then it knows implicitly how to actually do the appropriate fetching of the value. So instead of storing a value with the store operator, we actually do the tool notation to store the value in the value field. And now if we just name the value field, it fetches the value of its own on its own. Yeah, which means coming back to a similar picture. So assuming 55 is already stored in the variable in the field y, then again, yeah, we execute p to puts the base address on the stack. And now y does more things. It does the address calculation, and it also fetches the value. Yeah, so it's cell plus and then the fetch, so that 55 directly goes to the stack, and then we can print it. So that's the idea. And of course, we could have other fields than cell fields. We could have character fields and things like this, and 32-bit fields, 16-bit fields, floating point fields. And so my syntax is to use defining words for the fields that are inspired in some way by how you would do it in C, maybe with the difference that I think that unsigned should be the default way to do things. Maybe that's also force-like. If you do cfetch, then it normally does not do a sign extension. So cfetch is obviously an unsigned value, and or deals with an unsigned value. So you have these names for the types of the fields that define the appropriate field names, and you can of course define your own field definers, and all they share is that they implicitly fetch their value. Yeah, so and you use to plus to and yeah, to access to write the value. And sometimes you already you also want to suppress the fetching, and you just want to do the address calculation. Then you can use the RDDR, the address operator. And sometimes you want to know how large is the field actually, then you can use the size of operator. So that's the idea. And so you could do it like this and define, or this is part of the test suite, define a value flavored structure that has all these kinds of different fields. And just a demo, now you can then define an instance of that record, and you can store the appropriate floating point value to the field f if you want to. Right, so let's have a look at the demo, and let's see, we go here. Right. So at the top we have our example, and I change it slightly so that we have an unsigned int 16-bit value in the x field, and a signed 16-bit value in the y field. And but apart from that, it's the same. And let's see, if I include this, then it says, well, this is value flavored structures on a 64-bit system. If you load it on a 32-bit system, it tells you so. Yeah, but otherwise it will just work the same. And so we can do py dot as it, well, what is this? Undefined. I have to include, of course, the source code, which is point, include point.fs. And then I can say py dot, and I can say px dot, which might be something, but it's initialized with 0. Now, if I store something into x, yeah, and I'm reading px again, then it's a 16-bit value and then minus an unsigned 16-bit value, where -1 is not actually an unsigned number. But in a 16-bit representation, it would be 16-bit set. Yeah, 65,535, or px hex dot. Yeah, you see. Yeah, this is because I said the field is a 16-bit unsigned number. Yeah, and if I do the same with y, -1 p to y, and I do y py dot, yeah, it's just stores 16-bit, so it stores just ffff, but since it's a signed integer, when fetching the value, it does a sign extension to the native cell size of the forth system that I have, which is yeah, 64-bit, or maybe it's better to say hex u dot here. Okay, so what's this? Dot p. Yeah, you do it the right way. P y hex u dot. Yeah, you see it's sign extension. So it fetches 16 bits, all bits set, and then it does a sign extension to 64-bit. Yeah, and so it works fine in this setup. I can specify what type the fields have, and they do whatever is necessary to handle it in the correct way. So much for the demo. And well, we can work on this. How this is this done? So sometimes in other contexts, values are not called, or fields are not called fields, but in other contexts, they are also called slots. And so the word slot, colon, the name was free, and I took that. It takes the properties of a field and it creates the appropriate field word. Yeah, it's a field definer. And of course, we know we need to do the offset calculation. We want to know how large the field is. And then we want to get the field. Well, we want to get the value. We want to set the value. We want to increment the value. And then there are also alignment issues that you have to take care. So slot is a monster. You wouldn't normally use that, but you use it for defining the slot definers that you want. So like, for example, int 8 is defined, it's a field of size 1. No alignment is necessary. You do a int 8 unsigned with a cfetch, get the value. You do a write with a C store, and you do an increment with a C plus store, whatever this is. Yeah, and then this is how you do int 8, unsigned 8-bit value. If you have a signed 8-bit value, all you have to do is when you fetch, you have to do the sign extension. And this is what the code here, cfetch-s, actually does. Or if you have a floating point number, a floating point field, then in the system I'm looking at, it's 8 bytes large. You have to align the field with the f-aligned operator. If you fetch the value, you do it with ffetch. If you store it, you do it with fstore. And if you want to increment it, then you fetch the value, add 1 to it, and then you store, or add the value on the stack to it, and then store the value again, which is f plus store. Yeah. we put all the knowledge in these defining words of the slot definers so that we don't need to remember them. We just name a field to get the value, and we use the to or plus to notation to set the value, like we do with ordinary variables and values. The decision is yours. You can do it in a different way, but if you want to use value flavored structures, that is the idea behind it. And yeah, and as you see, we need to know about memory operators. Like we need to know fetch and fstore and cfetch and cstore. That's easy for 8 bits. Yeah, but if we want to fetch a 16-bit value, how is the operator called? Yeah, and if we want to do it sign extended, what then? Yeah, and they are not standardized, not even de facto one. There is no agreement on the Forth systems how to call these memory operators, 16-bit operators or 32-bit operators or maybe 64-bit operators. And different Forth systems use different words for different purposes. The worst thing that you have, so there's fetch S on SwiftForce for fetching a 16-bit value with sign extension. Is that right? Yeah, exactly. And then there's SW fetch on GForce that does the same. And but SW fetch is used in different Forth systems in a different way. So VFX, for example, returns the floating point unit status word, which has nothing to do with fetching a 16-bit value from the memory. And SW fetch on GForce does the right thing. So there is some agreement necessary to do portable programming of fetching values of different memory sizes in a portable way. Of course, you always can say, I'm just using a single Forth system and I'm done. I just stick with what it provides. But then you will have a tough time if you want to port it to some other environment. So it's necessary to agree on that. And there's an ongoing discussion in the standards committee. And there will be a public review of the ideas where all of you are asked to contribute and give your opinion and look at the proposal and see if this would be standardized. Would I be implementing this in my system, or would I use these kinds of words? So that's the approach that we are taking. Anyway, right. So I come to my conclusion. You can define records or structures similar to other programming language constructs with value flavored structures, which extends the idea of values to structures. And many people use values extensively, so it's only a natural extension to use them in structures as well. Get rid of fetch and store and use the to notation to put values in values, and let the values fetch their own content. Yeah, defining a structure should be very familiar and similar to the way that is already standardized structures defined with field, that where you have to do fetch and store on your own. Yeah, the idea is to have the definitions very similar, and also similar to the interfaces that you might want to access. If you read some C structure, then you want to one-to-one transcribe it to your Forth program. And we need to standardize memory access operators to do this, so that the implementation of the value flavored structure do not need to do lots of conditional compilation to decide whether one or the other operator is defined. It can be done, but it's tedious, and it only covers the system I looked at, and not the one where there is no idea. So that was what I wanted to talk about. Thank you very much for listening. And if you have any questions, I'm ready to ask them, answer them.
I have a question.
Sure.
How would you implement making it so that a value flavored structure both that you can call it like a regular word and get the value, but also get the also do to and stuff like that against it at the same time without some deep compiler black magic. Because when I implemented value for Zepto4, I essentially, it has to know about the internal structure of the code at a binary level to know how to set the value. It essentially has to extract the address from the value word and internally and use that. And that obviously is very non-portable. So how would you go and implement this in a portable fashion?
Yeah, well, you use high-level force, and then you can do that. I mean, we talked about the memory layout of the structures. It's memory cells, and you can do the appropriate address calculation, high-level force, and then you can apply the appropriate memory fetch operator. So
I don't mean like that. I mean, well, let's say you have a field name foo. When you call foo, it grabs the value out of the structure that you passed in. It's trivial to implement. But when you do to foo, how is it supposed to know that? How is the to word supposed to know that it's dealing with, let's say, a structure value rather than a normal value without, let's say, putting a special, let's say, a no-op in the value word that says to the to word, hey, this is a structure value and not a normal value.
I see. There is a magic number that is part of the field names, and you test the address whether you find the magic number there. So if you don't have kernel knowledge about your system, then you can't really decide what type of word you're actually looking at with to. And so what it currently does, it takes it, and then it tries to get a magic number from it. And if it finds that magic number, then you know it's a field address. And if not, then it's not a field address. And you cover this in a catch frame, so that even if you get an error by accessing a illegal memory operation, then you get know about that. So that's the idea. If you have kernel knowledge about the system, then you can maybe look into the code field and decide on the value of the code field what kind of word you have. And but if you don't have any information about the system, then you have to mark it in some way. But it's encapsulated, and you can change it if you want to do it on your system in a specific way. Then you can just go ahead and change that. Does this answer your question?
Yeah.
Okay.
I got one question. It seemed that great work, by the way. I think it's excellent. But the one downside I think I see, and I just want you to confirm that, is that the field names will clash with anything on the dictionary, right? So, for example, you couldn't have an X and a Y field in another structure like vector, for example, or if you had 0.2 or 0.3 for 2D and 3D thing, you'd have to come up with different names for the fields, right, to not clash.
Yeah. So there are actually, I believe, two solutions to that. One is use a naming convention. For example, in Lisp, you put the name of the structure as a prefix, and then a dash, and then the field name. That's also possible in Forth to do that. Or you could use namespaces, word lists, or whatever, so that you have to you have the field names isolated in the word list of their own, and then you have to have some mechanism to switch the word lists in an appropriate way, and so that if you name a structure, then the appropriate word list will be searched, and then you have to revert back. There's some research work on that by Manfred Marlow, how to do this in a clever way. Yeah, but you can't do this in standard Forth, and so I think with standard Forth you have to stick with either managing the word lists on your own or stick with the naming convention. Right, we're after the coffee break, and so my proposal is that we continue with Brett Nelson talking about news on the ESP32 Forth, and yeah, what's up? Brett, are you with us? Yeah.
All right, can you hear me?
Yeah.
All right, so I am going to give an unusual sort of talk in the sense that it's a talk about something that I'm still in the process of trying to do rather than I'm done with. And my intention with this talk is to sort of both communicate some of the things that I have a handle on and some of the things I'm struggling with. So. I gave a similar talk at SVFig a little bit ago, but I've inched forward since then, and this is sort of an updated version of that talk. Metacompilation is the idea of building a Forth from within another Forth, and using an additional set of words in Forth to build up the image of the new Forth system. And I think the main goal typically with metacompilation really is to do as much in Forth as you can towards the new system. This is in contrast to most, or I think essentially all of my Forths, with maybe one exception, have been more of the ilk where you build up the core of the Forth in either in assembly or in some other language, and then you sort of start the world turning from that point. So outside of the Forth community, this kind of thing is often called a cross compiler. Although I think it's a debatable point, I guess, whether what's meant by metacompiler in the Forth community really is one and the same as cross compilation. I think there is a subtle difference. Typically, when you cross compile in other contexts, what you're really doing is building up enough of a set of tools that are able to target some other system or the same system that you're able to recompile all of your tools. With Forth, oftentimes I think we try to take a sort of a shortcut, and I think metacompilation hits into that weird, peculiar shortcut of not quite building what would be a conventional cross compiler. The term metacompilation is overloaded. It sometimes is used to mean other things outside the Forth community, like lexer parser generators, things like that. So I think our usage of the term is sometimes a little confusing to folks outside the community. And then the other weird thing, and I think it's again because of that sort of short circuiting that happens in metacompilers, oftentimes they're structured to sort of restart the current system, but aren't always built with the goal of crossing architectures or crossing other assumptions about the setup of the system. So oftentimes the host and target will be assumed to have the same kind of dictionary format, that type of thing. And often I think this sort of interesting intellectual puzzle of how hermetic the relationship between host and target should be is where I get stuck, how isolated the two should be from each other. I think another kind of key facet of this is, because you're sort of bootstrapping a new system, you really have multiple dictionaries at play, and so at least at some level you need some kind of a notion of separation of vocabularies, and then you also have this peculiar constraint that you are often going to need immediate words to run on the host, because you don't necessarily have the target or can't, if the target is not the same architecture as the current system, then you've got you'd have to resort to something like emulation otherwise. And I think this bumps into some of the namespacing challenges that Forth has. I feel like vocabularies in Forth work, but there's something that isn't quite right. It's easy to have clashes, and I think metacompilers in particular run into some of the challenges we have in situations where you want to have multiple words in play that have this that have the same name. And I also think that where I've seen metacompilation work sort of elegantly are places like PygmyForth, where they'll use a scheme that typically has fewer vocabularies, oftentimes just a vocabulary for Forth words and a vocabulary for immediate words. There's a little bit of a quirk with them, I think, around repetition. You oftentimes need some of the immediate words to exist both on the host and on the target, and so you have this other sort of odd bootstrapping problem around how do you want to do this? Do you want to include the same source file twice or load the same block twice, that kind of thing? Or do you just want to repeat yourself is another option that gets taken. And then cleaning the whole thing up, oftentimes the transformation to sort of build up the target will sort of use kernel knowledge of the current system and may leave the current system in an odd state. So anyways, what started me on this path was a desire to build an x86-64 subroutine threaded target. Probably just will generate an alpha executable, and my current thinking was I would use source instead of blocks, and I wanted to avoid relying on vocabularies, or at least try to be methodical about thinking about sort of what the dependency order is. So this is my sort of fuzzy plan, and the notion is have a start marker, compile a bunch of words that are needed to be able to assemble on the target and as host words, and then define an alternate definition for dictionary, searching the dictionary, and then building on that, rebuild colon and bracket, and then compile that same set of words to be the core words on the target, and then from there compile the rest of the words and emit the new image, and should have a Forth come out the other end. And then some sort of cleanup. But it's a fuzzy plan, and so here's where I'm at. First, assembly, since I want to do a native target, PygmyForth has a fairly extensive assembler. I'm too lazy to do that much, so I'm going to just focus on a kind of a targeted assembler that only handles the subset of opcodes that I need. And then I'm going to do one sort of concession to performance. I'm going to do an optimization around the stack pointer being lazy in moving. So avoid emitting extra instructions to move the stack pointer. So I picked a set of register assignments that are, I think, a little bit similar to what SwiftForth uses. The main interesting thing here is just by using the base pointer and the stack pointer, using the base pointer as the data stack pointer allows for hitting some instruction encodings that can accomplish that optimization I just mentioned, and then caching the top value in RBX. this has the nice, also sort of happy accident that on for Linux at least, this doesn't collide with the set of registers you need to call into a syscall. So I can potentially leave my main Forth registers sort of alone whilst I call into a system call. Yeah, and it's just, there are these Linux system calls, and the thinking is to call them directly, and so do things like exit and write just by setting up the appropriate registers. So x86-64 instructions, they've got a fairly elaborate structure, a bunch of legacy prefixes, the rex prefix, and then the opcode, and this mod rm byte, and then potentially a scale index base byte and an immediate. And so typical example, here's a move instruction. I'm using the AT&T syntax, which I cringe at. I still, in my head, is still wired for the Intel syntax, but I'm using this because I'm using some of the Unix tools that use this syntax, so it's source destination. And there's the rex prefix, which is this indicator we'll talk about in a second as to what the how to use the extra capabilities that were added for 64-bit. And then the most interesting thing to observe here, you've got the opcode, this mod rm byte, so that's sort of the core of the opcode. And then for RBP, it works out that you'll typically have 1 byte that can be an offset relative to it. And so all of the places, almost exclusively where you use the RBP, the base pointer, to reference the data stack, you have, whether you want to or not, you're sort of paying 1 byte for the for an offset. And that's done mainly, I believe, as a concession to C-like languages to allow you to have your base pointer within a call frame and then be able to reference your local variables. In my case, I want to just avoid sliding that data stack pointer, which we'll talk about more in a sec. So that rex prefix is just a place that was added for 64-bit to be able to specify that you do want to use 64-bit, and then to provide 1 extra bit to expand the set of registers on x86 from 8 to 16. And so encoding that in Forth is reasonably straightforward. It's common enough because I'm primarily using registers that are in the lower 8 within the x86-64 set. Typically, I am just using rex w, which just means I would like to use a wide instruction, a 64-bit instruction. And then I've got the notion of being able to increment the return stack by a cell, and then set the return stack initially. And then this is the sort of handling for the data stack. And the data stack is more complex than the return stack because as I mentioned before, I wanted to do this optimization where I keep track of what the offset is to the top of the stack pointer, and only move it lazily when I have a moment where I want to use it. So I have these words that will assemble the instructions to do a large jump on RBP, and you can both add and subtract to it to get a little more range. And then I keep track of a variable called offset that is my offset relative to the current position of RBP to the actual top of the stack. And then the word balance will go ahead and put the stack, reset things back to 0 so that RBP actually contains the top of the stack. And then throughout the rest of the assembler, I can then increment and decrement where I intend the RBP to point at, and then make reference, and then that will save me 1 instruction per opcode, which we'll see later in the disassembly. So this lets me, do things like, for example, actually, let's see. These are just some plumbing words. Let's look at a real word. For example, in this implementation of dupe, and I've called it dupe tick because I don't want to clash with the dupe is used a little bit in the assembler, so I avoid it. So I'm incrementing the stack pointer, but not really incrementing it. So this plus RBP is moving where I sort of at compile time think of it being, but I haven't yet actually incremented it. And so then when I assemble an instruction for this move, I'm including this offset, and so that lets me know what offset I want to use. So you'll see these offsets sprinkled throughout, and I just described this in the comment as an offset plus 0. And so some words don't need the stack; they can just be done as increment and decrement. But other words, I'll continually reference this offset, which saves emitting that update. And so then I can build up all of the core words, and things like a plus operation, for example, end up being 2 instructions, one for the actual add operation, and then another to move the memory-based stack, the next element down into RBP, but notice that I don't have to adjust the position of RBP. And then similar thing for AND, OR, and XOR, and then invert and negate or don't move the stack. And then I've got the core comparison operations, and then exit. Here's an example where I'm balancing the stack. If I'm going to return from the current word, I want to make sure that I've now actually adjusted RBP. And so that's where I'll use that balance word to sort of reset things back. And then a NOP operation, here's at and store. And again, each of these is sort of saving that one instruction. Same thing withcat and cstore. Literals are a little tricky. If you want to support a 64-bit literal, there is an instruction that will actually take one as an immediate, but it's a fairly expensive word. I'm probably engaging a little bit of premature optimization here. There's instructions that will encode a 32-bit signed value and an unsigned value slightly more compactly. And so you can end up having a bunch of different cases to figure out what's the most compact way to do a literal. This is actually probably there are more examples of even more compact cases for, say, 16-bit values, but I've kind of limited it myself to 32-bit. Then the words that would be immediate, I'm realizing I'm missing an update here. These should all have immediate after them, but words for implementing the flow control, and each of them, of course, needs the stack rebalanced because you don't want to have the stack pointer in the wrong place when you're moving around in a loop. And then a syscall, this is probably a little overly Baroque, but here I'm using an offset relative to RBP, and rather than inline rather than doing the offset throughout these words, I went ahead and decided it was a good moment to balance the stack. You're going to call into a syscall. You probably don't want RBP to not be in its appropriate position. And so I have a single word that just assumes the sort of the maximum number of arguments you can pass into a Linux syscall of 6 of them. And then I've got plumbing to start building an ELF image. And the reason I build an ELF image is I want to emit an image that I can eventually execute. And so there's a header for the magic string that needs to be at the top of an ELF file, and then that's part of the overall ELF header, which includes a bunch of detail I won't go into, but basically it's allowing you to specify how many sections there are in the file, and in particular what you can do in an ELF binary is have a series of sections in the file that when the executable is run, they will be mapped into particular addresses, either with various permissions, so either readable, writable, or executable, or some combination of those. And so for my executable, I have only one of them. I load a single region of the image that I store to disk, and then I just set it to read, write, and execute, because this is, the easiest thing you can do for a chunk of memory. And so I just map it explicitly into 400,000 hex. And this is one nice thing with Linux. The executables allow you, or Unix in general, but ELF, I guess, in particular. Anyways, it allows you to explicitly specify the memory layout. And so where a Windows executable, you have to cope with situations like it might try to randomize where it wants to place you in memory. With an ELF executable, you can sort of say, no, I want this at a particular position. In fairness, the Windows thing is actually done as a security. It's actually sort of a security mitigation of a sort. You're trying to make it harder to have malicious programs know the layout of memory. And then I build up an image. And so here I'm just building up the top of the ELF header. Then I have the start of my one chunk of memory. Init is just a word to set up the stack pointer with a reasonable value. And then here I'm compiling just two syscalls, one to print out 3 characters from the very top of address 400,000, and then a second call to call exit. And then I end the image and emit it. So I'm going to briefly duck out here to my one marginal demo here. So I've got my code here in a little sort of a lot of the code that you just saw, and I am oops, build it from scratch. But, so I'm emitting a bunch of these words, and then blasting at an image. Here it is. It's only 344 bytes, but it doesn't do a lot. It prints out the first 3 characters of its own contents, which are the first characters of the ELF file. So it prints out ELF. Let's switch back to the slides. And so the next step, and I'm kind of partway there, is that I need to build up a dictionary, and I've vacillated as to the format to use. One challenge with a subroutine threaded forth is that the particularly on x86, it's not great in terms of performance to be intermixing code and data, and so I've been toying with putting the dictionary off in an array. 64 bits is a lot. Like if you do a hash on a word, you're not going to get a lot of collisions if you just hash it into a 64-bit value. And so the format I've at least currently been aiming towards is hashing the characters of the word, and then storing an address, and then just storing these as a series of pairs, and then using 00 as a marker up at the top. So I've got a simple hash function that sort of uses some weird primes and grinds down and just builds up, turns a string into a single number, and then that will let me implement a version of find that takes a particular vocabulary as a parameter, and then walk and see if I find a word in it or not. And then I'm currently assuming I will be doing something with a regular dictionary, a macro dictionary, and then a current dictionary. And so this is a word to add a word into that dictionary. And then I set up some space for that dictionary, those 2 dictionaries, and set up references to them. And then I've got a word that will generate into those dictionaries. It will parse the next word in the input stream and add it to the dictionary, referencing the current location. And then I'm also going to need number conversion. So I've got really simple number conversion that actually doesn't even handle negative numbers yet. So I'm sort of starting simple and then changing things as I need them. So we'll see. And then I've got the shape of what I want to do for bracket, but this is where I run into a problem, right? Bracket, what I'd like to be able to do is now go ahead and parse the next word out, see if I can find it in the macro dictionary. If I can't, then I go and look in the regular dictionary and then compile it. And otherwise, I assume it's a number. But on the host, I would like the macros, of course, to reside on the host, or else I'm going to not be able to successfully do things. And so this is the first spot I've hit where I'm feeling like I need to sort of bifurcate the word. And so I've struggled with this a little bit about sort of the right approach to take here. And so this is sort of one of these ordering challenges. The host, you need to use host macros, but you want to compile for the target. Do I need two versions of bracket? So struggle with this a little bit. And the ordering and name clash, I'm starting to hit the moment where it feels brittle to me. And that's it. And so I guess I wanted to highlight that as I sort of have gone through this thought process of trying to sort of wind my way through a metacompiler, it can be a little tricky. And I would love advice or guidance for folks who have more experience with metacompilers than I do. And that is it. Are there questions?
Excellent, Brad. Thank you. Thank you so much.
So yeah, I have a few comments and questions. So nice work. It looks really interesting from the look of it. I haven't followed everything in detail, but so my question is, so with the hash approach, wouldn't it lead that shadowing wouldn't work anymore? Or how is the hash supposed to work exactly?
So the intention is to be clear, not a hash table, but just a hash as a shorthand for the string. So it would still be an array of entries, but then you're walking backwards and finding the first match. So
all right. So I misunderstood because I thought that the hash led to an address where the dictionary entry would be.
Yeah, so it's not as a performance optimization, but just I'm trying to, and maybe this is another thing. When I try to go sort of as minimal as possible with these, I'll run into this issue that the set of words that you would need to do sort of correct string handling and walk up the dictionary, that feels like I'm bootstrapping a lot to get going, and so I oftentimes find myself looking for shortcuts there. And maybe it's misguided. I should just do the string comparison, do sort of do more to have a correct dictionary. But I think in my head I have always found the problem. I've always found it hard to keep in my head the sort of full through line for a fourth from scratch, whereas say color forth, for example, I'm able to sort of, I have a small set of dispatch routines and then a table and all of that. And so I think it's that kind of mode of thinking of how do I keep the dispatches as tight as possible. But maybe it's misguided. Maybe I should be, assuming, I need to be able to do a string compare and have that bundled up and all of that.
But the dictionary structure that you describe is similar to what Colorforce does. So it has a table of tokenized names and then a table of the associated addresses. And yes, it can do the shadowing. Brad, you might want to look for the hash algorithm. You might look at the FNV1A hash algorithm. I can put the name in the link in the chat. There's a large research on what you need to do to have as few collisions as possible in the space, and this is especially for hashing strings to magic numbers, to have as few collisions as possible, and it's very easy to implement. So you need one times, and that's it. Yeah. So I just put it in, and there's a wiki page, and there's also a page on Wikipedia, and also they have a project page.
And regarding the immediates, so because I'm swimming in the same puddles here. I like to swim in those bootstrapping and the metacompiling puddles, and so DUSKOS doesn't cross compile as much as CollapseOS. And in CollapseOS, I had the same kind of problems with immediates that you have, and it's kind of unavoidable. So you overwrite your immediate, you break. So you asked yourself earlier, oh, should I break the system or not? I think you can't really meta-compile without breaking your host, which you then need to forget after you're done meta-compiling. And then my approach to immediate is that since your immediate work cannot be executed on the target, then you know where you need to execute the immediate. It's always on the host, so you can shadow immediate words under target, and if they're immediate, you ignore them when you make the selection of what word you should choose. I'm not sure I'm making a lot of sense, but you can contact me if we can share on this subject.
Yeah. I think I see what you mean, but I might drop you a line. I see Francois has his hand up.
Yes. Have you made anything public yet?
I have not, although actually there's no particular reason that I'm happy to put it up if anyone's interested in taking a look.
I'd be interested for sure.
Yeah. I'll put it up on my GitHub after this. I'm mostly just lazy. Been fiddling on a local copy of it.
Thank you.
Will do.
Brad, I don't know if you can use, because my Ford is static, no have dictionary when running, but I do metacompilation, and I have a R3 interpreter right in R3, and in the Ford computer translation, I use not a hash for a word. I use a 6-bit for character and compress in 32-bit, and I have a version with then character in 64 bits, and limit the word in this size, and you don't need hash, and in this word, in this number, have the word 2, and you can decompress and show in a tokenized code, like a tokenized code with like color for Chacmore. I copy all these ideas from color for and translate. And this is code is in my repository. But I don't have the problem of dynamic dictionary and this, because I don't have dynamic dictionary, and the dictionary exists when compile and then discard.
Yeah, the 64 bits especially, it's very tempting. There's enough enough bits there to really keep a whole word. So it's yeah, always comes off as tempting to pack in the whole text. Yeah.
If you have a fixed set of words, you can use gperf and get a perfect hash.
Indeed.
No more questions. Anyone? Matteo Vituri or Jean Lagevart? No questions. Christian Hinze? No questions. Seglio Batuna or Cecil? No questions. So the next participant is a video of Jan. Do you want to make any questions for? Do you have any questions for Brad?
Can you hear me now?
Yes.
Okay. Maybe it's a pain in you or something. If I ask this, I wonder if the B-term Bluetooth kind of macro you have in ESP32 Forth, is that going to work? I'm still sticking with version 7.06.19, and the Bluetooth term doesn't work there. Is there? Yeah.
Is there a regression? Is it, or is this? I did move to a model where some of the features are you need to enable them. So is that? Yeah. So there's a if you look in the there's a set of files now in the zip file that include the different functionality, and I intentionally moved the Bluetooth functionality out to a separate header file, and all you have to do is move that header file in next to the INO file, and then it will add that functionality back in. So I think I talked about this previously at one of these sessions, but I did that because we were getting to the point where there were so many modules that there was some concern that it was the kitchen sink there, and so instead it's now structured so that some of the functionality is pluggable, and you can move them in and out of. I think there's a forgetting off the top of my head the name of the directory. I believe it's called optionals or something, and you can move one of those optional modules into. But if something is broken, please drop me a line. Let me put my email address in the chat, and please reach out if something is broken that you're hitting.
Okay, I have not tried it on a newer version, so I better find the latest stable version. What is the number of the latest stable version? Do you know that?
Let's see. Let me pull it up here. The latest stable. I would go. So I haven't. Yeah, it's been a while since I've stamped a stable one. So that I believe the long-term stable and the beta still don't have the pluggable stuff. So are you the latest stable is you can always find them here, but so yeah, actually you're actually hitting a fair point, which is I haven't so in the latest release, if you hit use the beta version, that one has the pluggable Bluetooth. But you're saying you've had a problem with B-term being missing in one of the earlier ones, or in the beta one?
That was in good old 7.06.19. That is very stable, yeah.
Yeah. And sorry, your B-term is not working there for you, or?
I can't remember what went wrong, but it's working like a macro when you say B-term, you'll execute something like 10 commands, and one of them is crashing the system. I can't remember which one, but it crashes, yeah.
Okay, well, I'll take a look at this, the stable one you say. Okay, let me take a look. Maybe I've got a bad thing in there. It's gotten also hard to test the matrix of all the things, and I don't use the Bluetooth terminal much myself, so I'll give it a check. And
if there are no more questions, I have a video of Bill Ragsdale I will share with all of you.
Well, good morning, good afternoon, good evening, Forth fanciers all around the world. By way of introduction, I'm Bill Ragsdale, the founding president of the Forth Interest Group, and I wrote Big Forth, but that is ancient history. Today, we're going to look at much more contemporary components of Forth. So, are you tired of trying to create yet another version of Forth, making small changes, making improvements, redesigning and playing the Forth game? Instead, how about thinking about writing an application? To inspire you, I'm going to relay the samples from 11 Forthers who have done good demonstrations and examples. These are all running in Forth, in Win32 Forth. We'll talk more about that as time goes on. And also, some are compiled on demand and other ones are turnkey. Turnkey meaning that they are .exe files. And Win32 Forth has the capability to take your applications and make them into a portable exe file. So let's explore these 11 applications today. I'll review them briefly and then we'll see them in detail. First, we're going to see a calendar, which is very flexible in its time frame. We'll see the help system for Win32 Forth, which was actually written in Win32 Forth. We'll see some simple examples of color and shading and graphics. We'll add some simple shapes and then see a very brilliant high-res graphic demonstration. Then we'll go on to games. First, we'll see the game of chess, then the solitaire game of Sudoku, and then Solipion, which is another graphic solo game. We'll look at an example of multitasking in Win32 Forth, a photo viewer, and a video viewer. So let's get into the demonstrations. First, I'll bring up the calendar demonstration. We come up with the IDE. We just simply hit F12. It compiles. And there we have our calendar. Right now, we're October 12th of 2023. But if I want to go to another month, I can simply move ahead. But if I want to go to another year, I can just click on the year as we have here. And now I'll click on a year again and we have decades. So now the entire calendar shows in decades. So I'll go to the decade 2040 to 2049 and pick the year. Let's find 2040. Actually, here is 2344. We are going to see the calendar for 2344. And amazingly, the first day of the year, January 1, will be on a Sunday. So you see here we have perpetual calendars that go backwards and forward over amazing periods of time. A beautiful application written in Win32 Forth. Next, we'll see the help system for Win32 Forth, which is written in Win32 Forth. Example of having split windows. Here we have 3 of them. We're going to have pull-down menu lists. We're going to look at the words. In this case, we're looking at the words of Win32 Forth. Pardon me, this is the ANS standard. Here are the words of ANS standard. Let's take a word that we're familiar with, such as dump. If I click on dump, I get in the top window, top center, I get a short definition of the word dump the parameters it takes, and an explanation. To expand on that, if I click on the little notebook, now we see the complete definition of dump along with its parameters, explanation, and the actual code. So here we have a very dynamic help system, not just rigid lists, but user-selected lists, and then linking directly into the source code. Very well done. We're into graphics now. This is a very simple graphic demonstration. I just hit F12, it compiles, and now we see we've generated some squares. These are divided into subpanels, and the subpanels are shaded. So this is a very good example on how to get started doing graphics in Forth. We'll see now a little more involved application. Again, I bring up the IDE, I compile, and the application runs and go to full screen. And we see now we have a rectangle with an inner rectangle within it, a dotted example of a dotted line, a point-to-point set of connected lines. Here is an arbitrary blue area, a couple of ovals that are shaded and outlined, and then finally the one in red, which has a very fine diamond pattern that is replicated across the surface. Very interesting technique, very useful to learn from. Now we come to one of my favorites. This is high resolution graphics, very high speed. I'll run the demo and then stop it quickly. What we see happening is colored lines at various angles, done randomly, running at full speed. You can see the tremendous graphic speed that Forth can offer. Let's clear that. Now we'll do another one. In this case, it's doing more interesting patterns, starburst, sunburst, triangles expanded. There is some sawtooth arrangements along. We'll clear that. We'll try it again. Again, you can see quite a variety of the geometries that are being explored. We come now to our first game. This is a game of chess we're all familiar with. It has very extensive instructions or information at the beginning on a revision history, on a help system, how to get it to work, how to use it. We'll compile this. And we see the board now in the lower left corner. The capital letters represent the white players. The lowercase represent the black. This is written in ASCII text format. I'll mention in a moment that there's a graphics version. We can either enter the plays move by move, or in this case for demonstration, I'll just type the word go, and the computer makes the first move, which is king's pawn goes to king pawn 4. The next move, based on hitting go for the black, we get the response of the king's pawn goes to king pawn 4. In this case, now the white has now moved the knight from the knight to the bishop 3, and the response will probably be the same, and the black makes the same response. Now, this game right now is being played according to what they call an opening book. There are a dozen or so opening books in here that are famous, well-known games in chess, and as long as the moves align along with those opening books, the play will follow. But you can deviate anytime you want. There are some commands to play automatically, so you can actually watch the game proceed at high speed to a final conclusion, either a checkmate or a tie. The missing element for today's presentation is the graphics. There is a graphics alternative for this that is three-dimensional graphics with the board and all of the players. However, due to evolution of Windows graphics, it's no longer compatible with the program, or should I say the program is no longer compatible with the graphics of Windows. So It was a very fruitful topic for one of you who's very much into the Windows capability would be to update the program and get it back into the graphics mode. But this is a very elaborate program. A tremendous amount of effort and thought went into its generation. We'll come now to the game of Sudoku. You're probably familiar with this. You've seen it in newspapers. In this case, you are tasked to place numbers on the grid. In each of these small subgrids, there are 9 squares, and you have to put in integers 1 through 9 with no duplication in the subsquare. But in addition, no duplication in any row or column. Well, I'll attempt to place a few numbers here. Let's take the number 7, and I'll see I was able to place it there properly, place it here properly. It's already in this square here. Let's see if I can place it here. No, that's incorrect. It's got to be placed there. We'll try that is correct, and so on. So you see, I've playing the game, placing the parts or the numbers one at a time. Let's try the number 5, and I think 5 will go here, and I believe 5 will go here. No, 5 is already in use in that area. 5 is good here. So we see how very good graphics use is made of this. There are quite a number of options on sizing, shading, and arranging the puzzle. And I believe there is an auto solution mode. I clicked on auto solution, and then the computer then calculated a winning solution to this puzzle. So you can play it individually. You can start with an empty, completely empty game. There's a completely empty game. You can copy it out of the newspaper, enter the starting point, and then play to your heart's content. The next one is Solipion. This is quite an interesting solitaire game. The goal is to put the 5th dot, completing 5 dots in a row. So I will click on the square, and you see we now have 5 in a row. This square, we have 5 in a row. We can join them together, 5 in a row, 5 in a row, and so on. On a diagonal, we had 5 in a row. And so on. You might think that it's fairly limited in the number of choices you can do, that at any given point you're hunting around here for what's the next logical move. But the computer itself will go into autoplay mode. And let's see how it fills out this board. Automatic play. There we go. So it starts the game each time identically, and then finds, by making a few random moves at the beginning, alternate ways of playing the game. Beautiful graphics, clever idea. And we'll quit that. Now we come to one of my favorites. This is multitasking. Win32 does not utilize multitasking internally for its own use, but the hooks and the tools are all there for multitasking. So I will simply hit F12 and compile the program. And now at the bottom, it says we have type demo 1 to start demo 1 or type demo 2. Let's start demo 1. And demo 1 will open 16 individual tasks. Each task is simply counting to 99 and then terminating. So we'll watch all the tasks running in sequence as they go to completion. You can see the very first task at the start is hit 99, down to get task 3 and 4 and 5 has reached 99. Further down, again, now we've gotten the last 3 open, and all tasks have run to completion. There is a progress report as this happened. The tasks are simply identified by an integer number that is assigned by the computer. And as you access each task, you just access it by its task number. So here is multitasking. You can utilize this in applications and in the first 3 or 4 pages of this, you now have a completely perfect prototype to build on for other applications. Now, the last one coming up, last one is next to last, is a photo viewer. So in this case, we can bring up a photograph. And I brought up the photo of John Scarney. I wrote a book on John Scarney, which is available on Amazon, and it's also available on YouTube. Look it up. It's John Scarney, More Than Magic. So this graphics program allows us to do simple graphical manipulation. We can rotate photos back the other way, flip vertically, horizontally, left, right, up, down. We can increase, decrease, and so on. By opening other photographs, here's John Scarney later in life. The first one when he was about 40 years old, and this one is when he's about 70. As you can see, he was a consumer consultant, and this is one of his promotional photos. And we'll bring up one more photo. Oh, it's a beautiful photo. Oh, that's me. So here's the slideshow. We can now click here and review slides in sequence. Or if I hit the next button over, we'll go into rotation and we'll automatically switch between slides as a slideshow.